3.5 billion miles from Earth lies one of the most captivating objects in our solar system. It's a tiny, icy world with the strangest atmosphere ever studied. It may have giant geysers, underground oceans. There's even a small chance it has primitive life. It's changing the way we look at Earth and our solar system. This is the former planet known as Pluto. Pluto sits on the edge of our solar system, 3.5 billion miles from Earth. Remote but not forgotten, for generations of school children, Pluto is the 9th planet. But on August 24, 2006, Pluto lost its planetary status. It was reclassified as a dwarf planet.
Pluto doesn't care what we call it. It doesn't care whether we call it it's going to be the same object whether we call it a planet or a dwarf planet or a minor planet.
Pluto has all of the characteristics of the other planets. In the same way that a chihuahua is a dog, just smaller. Dwarf planets are planets. They're a smaller variety.
Pluto sits on an exciting new frontier of space exploration. A state-of-the-art spacecraft is heading towards it at around 1 million miles a day. Scientists hope that it will shed new light on the formation of the solar system and even the birth of our own planet.
Every time we take a spacecraft and go by a new body, it turns into an entire world that is filled with fascinating phenomena that we would have never understood before.
The fact that Pluto is so far away, it's so small, it's so dim, and may represent now a whole new swath of real estate worth of objects, tells us that Pluto has a lot in store for us to learn about it.
Our story starts with Pluto's discovery. By the early 20th century, 8 planets have been discovered. Many assume that Neptune is the outermost. But astronomer Percival Lowell is convinced there is another planet out there, a massive planet whose gravitational pull is disturbing Neptune's orbit. He calls it Planet X, but it proves elusive, and for good reason. The giant planet theory is wrong.
The original motivations for searching for Pluto were based on bad data, basically. They just didn't have enough information then and good enough data to really solve this problem.
By 1929, astronomers at Lowell's Observatory outside Flagstaff, Arizona, have been searching for Planet X for 14 fruitless years. 23-year-old amateur astronomer Clyde Tombaugh joins the team and is given the painstaking task of comparing vast numbers of star-like objects. Tombaugh captures the images onto large photographic plates using a 12-inch telescope, small by today's standard. He's looking for tiny points of light that have moved across the night sky. Stars remain fixed while planets move. Tombaugh continues the search for over a year. Then, examining the plates taken on the 23rd and the 29th of January 1930, a faint object catches his eye. Flicking between these two images, he sees that the object appears to have moved. He checks and rechecks, making sure it isn't a comet or a blemish on the plate. It seems the young astronomer has discovered the astronomical Holy Grail, Planet X.
He also was extremely lucky to be looking at the right part of the sky at the right time. And of course, he had very keen eyes and skillfully able to pick out that small object as it moved across the sky.
Even though the giant planet theory turned out to be wrong, Tombaugh still found a planet. The new discovery is headline news. The planet is named Pluto, after the Greek god of the underworld. Based on their original miscalculation, they believe Pluto is bigger than Earth. Pluto officially becomes the solar system's 9th planet. Today, over 70 years later, Pluto is still pushing Lowell's modern telescopes and leading astronomers like Mark Buie to the very limit of their abilities.
Even with modern day tools, it's a difficult job to find these objects, and you have to look at a lot of sky, a lot of data, use the computers, use all these tools, and we work down at the very limits of what our data and our telescopes can do.
For decades, even the most basic questions about Pluto remain shrouded in mystery. And the most basic of all, its size. The breakthrough comes in 1978 with the discovery of Pluto's largest moon, Charon. It was a stroke of luck, as no one thought Pluto had any bodies nearby. Astronomers were able to estimate Pluto's mass by looking at its gravitational influence on Charon.
Now we know what the mass of Pluto is, and all of a sudden it goes from this vague, poorly known place to now you know something about it and can start putting it in context.
The results are surprising. Pluto is not larger than Earth. In fact, it's smaller than our own moon. Side by side, Pluto and Charon only cover the width of the United States. But for astronomers, the biggest mystery was why Pluto appeared to be on its own. In 1951, Gerard Kuiper theorized that Pluto was a remnant of a once massive belt of objects circling the outer solar system. This region of space became known as the Kuiper Belt.
Kuiper predicted a huge empty space where we see the Kuiper Belt. He thought that Pluto was a massive body that would have swept out all the objects there. And in fact, that's not the case at all.
Back then, Kuiper didn't know that Pluto was too small to have had this dramatic gravitational effect on other bodies. Maybe there was a belt of icy objects out there, just too small for them to see with their limited telescopes.
By 1985, it did seem kind of odd to me, and to other people, I think, that the outer solar system would be a very empty place, where essentially nothing was known except for Pluto.
Mauna Kea, Hawaii. In 1988, Professor David Jewett of the University of Hawaii's Institute for Astronomy begins a dedicated hunt for another object beyond Neptune. Despite harnessing the latest digital technology, the task of looking for a tiny asteroid-sized object at the far reaches of the solar system is a daunting one. A bit like finding a grain of rice on a mountainside, as Jewett demonstrates.
To give you an idea for the scale of the Kuiper Belt relative to the orbits of the planets, I've laid out the solar system using various kinds of fruit and vegetables. So we have a ball to represent the sun. Next to the sun, which is the center of the solar system, we have the rocky planets. So we have to go out to 5 astronomical units, 5 AUs, to find Jupiter, the biggest thing in the solar system except for the sun. Then we go out from Jupiter is Saturn, located at 10 AU. Out from Saturn is Uranus at 20 AU. Uranus is the first of the ice giant planets, and Uranus has a near twin. It's called Neptune. Neptune is over here at 30 AU. And then just beyond Neptune comes the famous Pluto, represented here by a tasty macadamia nut. And Pluto moves in and out from the sun, but it's roughly located at 39 AU. So we'll put that back where we find it. Kuiper Belt starts roughly at the orbit of Neptune and goes out to larger distances. So we can represent that by grains of rice from this bag, which I'll drop on the ground, These are Kuiper belt objects falling in space, and here they go, but in fact they go very far out. They go out in this direction, and in fact it goes out so far that I can't throw it far enough. It goes out to the hill in the distance, far beyond me.
But in 1988, all this is speculation. It's just a theory. There's no hard evidence of other objects in the Kuiper belt. Dave Jewett continues believing there have to be more Kuiper belt objects out there, somewhere. For 4 years, he toils in the thin air of Mauna Kea's high-altitude observatories. He has no idea how big or bright any of the objects might be. Then in late November 1992, he and his colleague Jane Liu spot a faint moving dot in the sky.
It was a very, very definite object, far above the noise, far above the threshold of uncertainty. We're completely sure that we found the first really slow-moving thing in the solar system since Pluto.
And it's small, just 140 miles across. Its diameter is just a tenth of Pluto's.
If we were able to find one body in 0.1% of the sky, which was the case, then we knew there must be something like 1,000 times more objects than we'd found.
Jewett's discovery has astounding implications. Now astronomers know there are potentially thousands of icy bodies, escapees from early planetary formation, orbiting out beyond Neptune. And Pluto is just one of many. Perhaps Pluto is not a planet after all. The discovery of thousands of objects in the Kuiper belt opens up a whole new realm of planetary possibilities. Pluto no longer marks the edge of the solar system. There are hundreds of objects in the Kuiper belt waiting to be identified, and astronomers are scrambling to find the great prize, an object bigger than Pluto. In 1998, Professor Mike Brown at the California Institute of Technology joins the hunt. At the Palomar Observatory in Southern California, Brown's team embark on an extensive search.
We had started this project of scanning the skies 7 years earlier, and with the idea that we wanted to see if there was something bigger than Pluto out there. We thought there just had to be.
Unlike Tombau's manual method, the team uses a computer-controlled telescope with digital cameras to take hundreds of images across the whole sky.
Clyde Tombaugh used photographic plates, and he would take 2 photographic plates and compare them and look for something that moves. We now use the digital cameras instead, and the computer does most of the work that Clyde Tombaugh did.
On October 21, 2003, the computer records a snapshot of space and gives it a code: 2003 UB313. But with such a backlog of images, 2 years pass before Brown has a chance to review it. Like Tombaugh, it's now down to his skill and judgment to spot one significant object among thousands.
And suddenly this big bright object appears on my screen, and my very first reaction, what did I do wrong? Something must be wrong here. This can't be right. And I checked everything, and realized, no, this is really there. And I immediately picked up my phone and called my wife and said, hey, I just found a planet.
2003 UB313 is around 70 miles wider than Pluto. And though it's 3 times further out than Pluto, it's one of the brightest bodies in the Kuiper belt. Astronomers call it Eris.
We knew immediately, once you start discovering other objects beyond Neptune and look at the distribution of their sizes and the rate at which you're discovering, it was just a matter of time before you would find one larger than Pluto. And in fact, that's happened.
I never actually really thought we were going to find that one bigger than Pluto. So it It was sort of a fun moment.
For Brown, Eris is the discovery of a lifetime. For Pluto, the implications are serious. No longer alone, and not even the biggest or brightest body beyond Neptune, can we still call Pluto a planet? One of the first to publicly question Pluto's status was director of New York's Hayden Planetarium, Dr. Neil deGrasse Tyson.
We first opened to the public in the year 2000, not including Pluto among the ranks of the other principal objects in the solar system. And we got raked over the coals by the New York Times had a page one story saying Pluto not a planet, only in New York. Okay, and then I got like hate mail from third graders, ever since.
Tyson leaves Pluto out from the display because it doesn't fit into his two main planetary categories: the inner rocky planets and the outer gas giants.
Pluto's always been a curious object, primarily because we've known so little about it.
Defining a planet is not as simple as it seems. Take Neptune's moon Triton, for example. Although it's 40% bigger than Pluto, Triton is just a moon. After much deliberation, the International Astronomical Union came up with a new definition. Planets now have to meet three basic criteria. They have to have sufficient mass for gravity to contract them into a sphere. They have to orbit the sun and not some other body, or else they would be moons. And lastly, they have to clear the material around their orbit. Unfortunately, Pluto fails to meet one of the criteria. It does not clear the neighborhood around its orbit. On August 24, 2006, Pluto is reclassified as a dwarf planet.
The word planet hasn't been defined since ancient Greece. Back then there were 7 planets: Mercury, Venus, Mars, Jupiter, Saturn, the Sun, and the Moon. And it was never redefined to accommodate our new understanding of the solar system.
Pluto may have lost its planetary status, but it hasn't lost its intrigue. The more scientists learn about Pluto, the stranger its story becomes. Unlike all the other planets, Pluto's surface is covered with exotic ices, such as frozen nitrogen and methane. There are at least 3 moons orbiting Pluto, a planet 2,000 times less massive than Earth. And Pluto's eccentric orbit is more like a comet's. For almost 60 years, it was also impossible to tell whether Pluto had an atmosphere. And when scientists finally get a chance to look, they discover something remarkable. Pluto's atmosphere is unique in the solar system. It's causing the planet to shrink. Pluto, once an isolated planet, the 9th in our solar system. Now stripped of its planetary status, Pluto is just one of thousands of icy bodies in the solar system's furthest reaches. It might not be alone, it might not be a planet anymore, but Pluto is still intriguing. And as scientists unlock the mysteries of Pluto, they're discovering a world full of puzzles and surprises. Astronomers figured out that Pluto was cold and that its surface was encased by ices, but for 58 years, they couldn't tell whether it had an atmosphere. No telescope on Earth was powerful enough to confirm this basic phenomenon on an object 3.5 billion miles away.
Even using the most powerful telescope available to astronomers, the Hubble Space Telescope, which is a fantastic instrument, Pluto just looks like a barely resolved, very pixelated object. We just can't see much detail.
On June 9, 1988, NASA's Kuiper Airborne Observatory takes to the skies. Astronomers board this specially equipped high-altitude plane on a journey to the Earth's stratosphere. Their mission is to search for evidence of an atmosphere on Pluto by observing a strange celestial phenomenon. The only way to identify an atmosphere on a remote body like Pluto is to observe it during a type of eclipse known as an occultation. When a celestial object, like a moon or a small planet, passes in front of a star, starlight is sharply cut off if there is no atmosphere present. But if the body does have an atmosphere, the starlight behind it gradually dims as the body passes in front. On board the plane, high-powered telescopic instruments record the critical moment.
Hey, wow, okay. I think that thing has an atmosphere, guys. Yeah, yep, atmosphere.
Pluto has an atmosphere. It's similar to Earth's, but extremely thin.
Pluto's atmosphere has many of the same chemical constituents as the Earth's atmosphere, but there's very little of it. If we took all of Pluto's atmosphere and we cooled it down even further than its current cold temperature, and it collapsed onto the surface as a frost or snow, we'd have snow up to the kneecaps.
But how does Pluto have an atmosphere under these frozen conditions? The answer turns out to be linked to its eccentric orbit. Most planets take a roughly circular route around the Sun, but Pluto follows an extreme elliptical path. Its orbit carries Pluto as close to 2.9 billion miles from the Sun and as far out as 4.6 billion miles. By contrast, Earth's distance from the Sun varies by just 3 million miles. Pluto receives almost 3 times more sunlight at its closest point to the Sun than at its furthest point. As it moves towards the Sun, Pluto's surface ices turn into gases. The result is a unique atmosphere. It comes and goes. Mark Buey of the Lowell Observatory in Flagstaff, Arizona, explains that Pluto's strange atmosphere is, in effect, turned off and on by the Sun.
This is a little bit like what the atmosphere of Pluto might be like when Pluto is closest to the Sun. And then as the Sun goes away from Pluto, this is what happens. We're going to stick this balloon into this really cold liquid, and the balloon starts to collapse and shrink and get smaller and smaller and smaller as the pressure of the gas inside goes away. And hold it here long enough, and now I have a totally collapsed balloon. Now you'll notice as I pull it back out, it's starting to warm up again. There's actually liquid air inside there. And the gas starts to expand and swell up. And this is kind of what happens with Pluto's atmosphere, we think, over the course of its year. At perihelion, or when it's closest to the Sun, you have this big atmosphere. And then when it gets furthest away from the Sun, the atmosphere shrinks and could maybe even disappear entirely.
No other known body has such a radically fluctuating atmosphere. And the more scientists study it, the stranger it becomes. Fran Bagenal, professor of astrophysical and planetary sciences at the University of Colorado, thinks that Pluto looks like a comet because it has an atmosphere that leaks into space. Pluto's gravity is so weak that its atmosphere stretches hundreds of miles above the surface.
Similarities with the comet are that the weak gravity of Pluto allow the atmospheric gases to escape. And so, as Pluto gets closer to the Sun, you have greater evaporation and more material escapes. Indeed, it looks very much like a comet in that respect.
When a comet travels towards the Sun's heat starts to affect its icy surface. Ices turn into gases and are blasted away, giving the comet its distinctive tail of ionized gas and dust. Although Pluto doesn't release dust like a comet, it does leak up to half a ton of atmospheric gases every second. And this leads scientists to a startling conclusion. Pluto must be shrinking. Each time it heats up, it gets a little smaller. During our solar system's lifetime, as much as 18 miles of Pluto's terrain may have been lost to space.
And so as a result of this, we expect there to be a considerable variation in the surface, hills and valleys that have evolved over the age of the planet.
Hidden for decades, Pluto's strange surface is obscured to even the most powerful telescopes. But there is a special type of device that can bring it into focus. The infrared spectrometer reads the distinctive reflective signature of Pluto's surface. Using this technology, scientists can piece together a remarkable picture of the strange world of Pluto. Spectrometers tell us that Pluto's surface is covered by exotic ices. Temperatures on Pluto drop to a chilling -396 degrees Fahrenheit, so that nitrogen, methane, and carbon monoxide exist as frozen solids. The gases we breathe, see through, and move through on Earth make up Pluto's rocks, plains, and hills. Astronomers think that around 30% of Pluto is made up of ices. Beneath the exotic ice-covered surface sits a water-ice mantle. But is Pluto just a frozen world? As scientists investigate this puzzling dwarf planet, an intriguing possibility emerges. Could there be an ocean hidden beneath its surface? Could the existence of ice and liquid water on Pluto provide further evidence that the Kuiper belt was a source of Earth's water? Scientists believe that Pluto-like worlds may have played a fundamental role in bringing water, the vital ingredient for life, to Earth. In the outer solar system where the sun's influence is weak, water ice is abundant. But could Pluto also have liquid water? Professor Bill McKinnon of the Washington University in St. Louis thinks so. He believes that beneath Pluto's frozen surface, there could be an ocean. McKinnon believes that water on Pluto could exist in liquid form due to the presence of ammonia, which acts like antifreeze. If he's right, water could remain liquid at temperatures far lower than those of the Antarctic.
Bodies like Pluto can actually have oceans. Not oceans on the surface like on the Earth, but oceans down below. And I have basically Pluto right here in this glass, and I can add the water and something like ammonia that would be inside Pluto.
Add ammonia to water, and the freezing point plummets to nearly -142 degrees Fahrenheit.
And to make it look more oceany, although we have no idea what the color of Pluto's ocean would be, we'll add some food coloring. Now out there in space, you're a long way from the sun, so it's cold. And so the top will freeze, like on a lake or in the Arctic, and you'll actually start freezing from the top down, and you'll make a thicker and thicker layer of ice, and I'll start it off by adding some ice at the top, which will float. And then, because we can't actually go into deep space, we'll put it in the freezer. But I put an earlier version of this a couple of hours ago, and this is sort of what you'd actually get. You'd actually see an icy layer floating on, I can jiggle it a little bit, a liquid layer that actually won't freeze.
After 2 hours in the freezer, the ammonia keeps the water liquid. But turn the temperature down below minus 142 degrees, and even ammonia-rich water freezes. On Pluto, surface temperatures are a mind-numbing minus 390 degrees Fahrenheit. At temperatures this low, every drop of water should freeze. So for water to remain liquid under the surface, there must be another force at play. A force that scientists believe lies deep inside Pluto's inner rocky core. Here there may be radioactive substances which generate heat as they decay. This heat could raise Pluto's subsurface temperatures to the critical level where ammonia-rich water can exist. It's a tantalizing theory, because whether in liquid or frozen form, the presence of water on Pluto and its Kuiper belt neighbors could hold the key to one of our planet's greatest mysteries: the origin of its oceans. One popular theory suggests that comets, which are rich in water ice, may have delivered water to Earth. But Dave Jewett thinks comets may not be the only source of Earth's oceans. Jewett believes Pluto-like bodies in the Kuiper belt may also have played a part. It would take roughly 1 billion average-sized comets to deliver Earth's water, or one single ice ball 600 miles across. No comet this large has ever been discovered. But in the Kuiper belt, there are between 50 to 100,000 ice-rich objects larger than 60 miles in diameter, and dozens at least 600 miles across. At the dawn of the solar system, astronomers estimate that the Kuiper belt was around 100 times more massive than it is today. Sometime in the past 4 billion years, the Kuiper belt has shrunk.
Several tens of Earth masses, even up to 100 Earth masses of stuff, originally was present in the Kuiper belt and then was lost by some process that remains mysterious.
Could this loss coincide with the creation of oceans on Earth? This is Neptune, the 8th planet and the Kuiper belt's closest gas giant. Computer simulations show Neptune's huge gravitational field may have dislodged Kuiper belt objects, sending them spiraling toward the sun. Parts of them may have collided with Earth.
We know there was a period of time when there was just stuff slamming in all over the place. And that had to hit the Earth too. It's possible, entirely possible, that those objects were Kuiper belt objects, which are full of ice and water. Most of the water is hanging out in the outer solar system, and all the rocks are in the inner solar system, but maybe by these stirring events, you can kind of bring these two areas together.
If the theory is correct, objects like Pluto and the Kuiper belt played a part in delivering Earth's water, vital to all life as we know it. Pluto is slowly yielding its secrets, shedding new light on our solar system. But incredibly, almost 80 years after its discovery, we still don't really know what Pluto looks like. Despite powerful modern telescopes, there are no detailed images of Pluto. These, taken in 1994, are the clearest to date. They were captured by Hubble, the space telescope that escapes the distorting interference of Earth's atmosphere. The largest point of light in the center is Pluto. Its largest moon, Charon, is next to it. To construct a global map of Pluto's surface, Mark Buey turns to Hubble's infrared images.
Each one of these images represents one picture taken with the Hubble Space Telescope. You stitch all those pictures together into a uniform map, which then I can manipulate and make it look like a globe.
This composite globe shows a reddish surface with patches of light and dark, evidence that Pluto has a varied landscape. At the solar system's outer limits, beyond the reach of even the most powerful telescope, Pluto remains shrouded in mystery. But not for much longer.
You either need a bigger telescope or you gotta go there. And so, we're going there.
Right now, a sophisticated spacecraft is racing towards Pluto at around 1 million miles a day. It's ETA 2015. January 19th, 2006. The Atlas V rocket blasts off from Cape Canaveral, Florida. On board, the New Horizons spacecraft. It's on a 9-year journey to Pluto and the Kuiper belt. This is a voyage into the unknown. Since NASA's inception in 1958, its missions have provided stunning pictures and vital scientific information about our solar system. Some have even involved robotic landing vehicles to examine and explore these new worlds up close. NASA has sent spacecraft to every major body in the solar system, except Pluto. Pluto is still waiting to be explored. In the first ever image of Pluto taken almost 80 years ago, the planet appears as a tiny pinprick of light, no brighter than a distant star. Even the latest images, captured by the Hubble Space Telescope, show Pluto as just a blurred ball of light.
Pluto is so far away and so small that Hubble's capacity to see detail is greatly limited.
To get a sense of what it's like to try and see Pluto, the best thing to do is to think about if you were to look at a ping pong ball, someone was to carry it 25 miles away.
An important clue to Pluto's appearance comes from data gathered by another mission to the outer solar system. In 1989, NASA's Voyager 2 skimmed past one of Neptune's 13 moons, the mysterious Triton. This flyby provided astronomers with a tantalizing glimpse of what Pluto might look like.
This icy moon, this large icy moon, that's very much a companion to Pluto, similar size, similar part of the solar system, and maybe had a very similar origin.
Astronomers theorize that many billions of years ago, Neptune slung Pluto outwards and dragged Triton towards it, taking it captive as a moon.
Triton is just like Pluto, but it got captured by Neptune billions of years ago. If we were to fly over Pluto, we would see impact craters and volcanic calderas or collapsed craters, and maybe even active venting or plumes, because we see these things on Triton.
Triton's strange landscape suggests that Pluto could be a dramatic place. And on Triton, the most dramatic features of all are geysers. Voyager 2 captured these remarkable images, evidence of geysers that last for up to a year and spurt gas and dust up to 5 miles high. If there are similar geysers on Pluto, astronomers predict that they would be driven by the sun. Although the sun is over 3.5 billion miles away, its heat may still have the power to affect the ice beneath Pluto's surface, turning it into gas. Pockets of subsurface gas would build up and eventually burst through Pluto's frozen surface as geysers. Will Grundy demonstrates how even a small increase in temperature produces a large geyser.
Okay, we're going to put liquid nitrogen into this plastic bottle, and it's very cold at 77 degrees above absolute zero. So as soon as it comes into contact with the hot environment here with the sun shining and the warm air, it starts boiling like crazy. And as it boils, it's going up into gas. giving off a huge amount of gas. And as soon as I screw the lid on, the gas has nowhere to go except up the tube in the lid and out through this cooler full of ice to form our simulated geyser. And here it comes. On the surface of Pluto, don't know what the scale of those geysers would be, whether they'd be very small like this one or maybe a kilometer tall.
Such mysteries will be solved on New Horizons' arrival in 2015. The spacecraft's camera has already been tested 6 months into its epic journey, capturing perhaps the greatest volcanic eruption ever witnessed in space. "76 years after Pluto's discovery, and after 17 years of research and development, NASA's New Horizons spacecraft sets out for Pluto. Traveling at around 1 million miles a day, it's on a 9-year, $700 million journey to reach Pluto and reveal its secrets. New Horizons' chief scientist is Hal Weaver.
Where we are right now is mission control for the New Horizons mission to Pluto. This is where we watch all of the activities that are occurring on the New Horizons mission. We have over here to the left a depiction, a software prediction of exactly where the spacecraft is, where it's pointed. We're following and it's on its path to Pluto.
In early 2007, New Horizons passes Jupiter, using the planet's intense gravity to boost it toward Pluto. It took the opportunity to test its camera on Jupiter's largest satellite, Io. The results were spectacular. This footage, captured by New Horizons' long-range reconnaissance imager, shows the actual eruption of a volcano on Io's surface.
We were just lucky and happened to catch it when one of the major volcanoes was active. It had spectacular plumes. Volcanic debris was flying up for a couple of 100 miles above the surface.
It's a stunning but short-lived encounter. New Horizons soon leaves Jupiter behind. Traveling at over 8.5 miles a second, it's the fastest spacecraft ever launched. It's going so fast that after its 9-year journey, New Horizons will only have a day and a half to see Pluto close up before disappearing deeper into the Kuiper belt.
And that's great for getting there early. But on the other hand, of course, that means that everything is really sped up as we fly by, because unfortunately, we can't just go to Pluto, put on the brakes and stop and hang around for a while. Roughly 3 months out, we're going to have resolution that's better than Hubble, and then it just gets better and better and better as we get closer and closer. But for those last 24 hours where we have this really high spatial resolution where we can see football field-sized features on the surface of Pluto, that all happens very quickly. We're just going to fly by and then just by Pluto and on deeper into the Kuiper belt.
With such a short window to capture data, the team must test and retest the instruments throughout New Horizons' 9-year journey.
Every year, for about 2 months, we're going to wake the spacecraft up and do some testing. Some observations of celestial objects and some commissioning testing of all the instruments to check them out, to make sure they're still performing and they'll be ready to go when we finally get to Pluto in July of 2015.
Ready to answer some of science's most fundamental questions.
The delivery of organic material and water from the outer solar system to the inner solar system may have played a pivotal role in the formation of life on the Earth.
It's just one of many questions about the solar system and its formation that scientists hope New Horizons will help answer. But above all, when New Horizons arrives, astronomers are expecting the unexpected.
I think the most exciting things that we're going to learn from New Horizons are all those things that it never even occurred to us to ask. And suddenly you go there and you realize, wow, we didn't know anything.
One thing is certain. The arrival of New Horizons will be the astronomical event of the 21st century.
It's a whole new kind of world. It's a planet I think everyone has tried to imagine. It's a frontier world. It's going to be the cover of the Rolling Stone.
And perhaps most fittingly, the spacecraft carries the ashes of the man who started the journey to Pluto almost 80 years ago, Clyde Tombaugh. This is a journey to one of the solar system's most puzzling, most mystifying worlds. Once the 9th planet, now a dwarf planet, an isolated oddity that became one of many. A frozen wasteland that could be home to giant geysers and underground oceans, and even possibly to primitive life. With so many twists to Pluto's story, who knows what surprises lie waiting to be discovered? Waiting for New Horizons' arrival in July 2015.
Outer space holds a weapon 100 million times more powerful than an atomic bomb. One strike, and it could black out a continent. From the space age to the Stone Age, in a flash. The weapon isn't man-made. It's our sun.
It's always a question of when the next one will happen. It's not a question of will they suddenly go away.
We've been hit before. We're in its sights again. Quebec, March 13th, 1989. The city is in the grip of winter. Temperatures are below freezing. Suddenly at 2:44 a.m., a 100-ton transformer on the Montreal power grid overloads. Blackout. The city is plunged into darkness. 6 million people left powerless. Astronomer Sten Odenwald explains how the night unfolds.
All the lights went out, quite literally. It only took about 90 seconds for fully operational to complete blackout conditions.
At dawn, the thermometer reads just 8 degrees, and the power's still out. Life or death work runs on emergency generators. The blackout lasts 12 hours. But the disaster could have been much worse. If not for a few transformers in the US, millions of Americans might have lost power too.
With only a couple of more components damaged, the entire East Coast would probably have gone down as well.
But what caused the transformers to overload so violently? Why did Quebec plunge into darkness? This wasn't a terrorist attack or human error. The culprit wasn't of the Earth. It was the result of a gigantic explosion 93 million miles away on the sun. Three days before the power network collapses, astronomers at the Space Weather Prediction Center in Colorado monitor an active region on the sun, when suddenly, a giant explosion bursts from its surface. A white flash thousands of miles across and millions of degrees hot. 93 million miles later, a huge wave of radiation slams into Earth's atmosphere. Colored lights dance across the night sky from Alaska to Mexico. Quebec is hit by an invisible but immense natural phenomenon. A solar storm. An explosion of the sun so awesome, and a wave of energy so huge, it's almost impossible to measure. Space weather scientist Joe Kunches is blown away by the scale of these storms.
Billions or trillions of tons of matter is thrown off the sun at 1 million or so miles per hour. And I think it bodes towards the difference between terrestrial weather scales, where you might have wind speeds in the extreme of hundreds of miles an hour in a very strong hurricane or a tornado, to looking out at the solar wind, and the solar wind typically is 1 million miles per hour.
The solar storm that hit Quebec is the worst in living memory. But worse may strike the Earth in the future. And next time, we might not be so lucky. The sun is capable of producing storms that could black out whole continents. North America would be crippled.
Losing the electric power grid, even temporarily over an entire continent, is a major disruption to the way we operate in the 21st century.
Our lives are more complex and technologically advanced than ever before. But the freedom technology brings us could also be our downfall. Anything relying on the power grid when a solar storm strikes is vulnerable. But what causes a solar storm? How do they wreak so much havoc here on Earth? And is there any way to protect ourselves from future attacks? Scientists need to unravel the mysteries surrounding the sun and reveal the anatomy of a solar storm. The investigation begins 93 million miles away. The sun is a 900,000-mile-wide ball of gas, mainly hydrogen. It's so vast, you could fit over 1 million Earths inside it, with room to spare. All the sun's energy is generated deep within its heart, at the core. Temperatures here reach 27 million degrees, thousands of times hotter than Earth's most extreme forest fires. Every second, millions of tons of hydrogen are converted into helium. This nuclear fusion produces over 5 million tons of energy. The sun radiates more energy in 1 second than the world has used since time began. The byproduct of all this energy is vast amounts of magnetism. Huge magnetic fields loop across the surface. They bubble up from the core and punch hundreds of thousands of miles into the solar atmosphere before plunging back down again. These arcs are so vast, the Earth could fly through one, with 100,000 miles to spare on each side. On planets like the Earth, every part makes a full revolution around its axis each day. But the sun is a dynamic ball of gas. Its equator rotates in 25 days, but the poles take 35 days. The magnetic loops stretch and distort as it turns. Along each loop flow billions of tons of superheated plasma, electrically charged protons and electrons. A single loop contains the energy equivalent to 10 million volcanoes erupting at once. These loops are sometimes the first sign of an impending solar storm. Professor Paul Bellin wants to find out how these loops lead to a solar storm. So he recreates the surface of the sun in his lab.
We have the main ingredients of what goes on in the sun. We set up a magnetic field that is arched. We have a plasma there that can conduct electricity just like the plasma on the sun. And we drive an electric current along the arch just like on the sun.
With all the ingredients of the sun in place, Bellin passes an electric charge through the experiment. Bellin's work shows these arcs are unstable. They twist and stretch in all directions. When they collide, they short circuit, like crossed wires. All their energy is released in a spark, a white-hot flash. The same phenomenon we see on the sun. A solar flare.
It's a little bit like seeing a hurricane develop. You can see the precursors of something that might blow up on the sun. You have currents, magnetic fields, the currents make forces, and if they add up in the right way, you can get very powerful forces that can cause these structures to blow up.
Bellin's lab flares release only a small amount of energy. If the energy packed into a solar flare was unleashed on Earth, the explosion could level whole cities. The shock waves would be felt on the other side of the Earth. Nearly all life would be wiped out. Far stronger than the world's nuclear arsenal.
The smallest of the flares are more than 1 million nuclear bombs going off. The largest ones are 1 million times 1 million of these bombs going off.
Dr. Carol Shriver studies the power of solar flares.
A large flare is a vast amount of energy. It has no counterpart on Earth.
One solar flare packs enough energy to power America for thousands of years. In 1997, NASA captures this image of the sun's surface the moment after a solar flare explodes. It shows a shock wave, a ripple, racing thousands of miles across the surface. It travels so fast, it could circle the Earth in less than a minute. A solar flare packs a huge punch, but it isn't responsible for Quebec's power failure. It is the first stage of a devastating onslaught. Like the flash from a gun, it's the bullet that follows which causes the damage. Behind nearly all solar flares is a gigantic cloud of radiation, and in its sights, Earth. But its first victims are in outer space. For years, space scientists have known of the threat posed by solar storms. But the sun is unpredictable, and sometimes even NASA can be taken by surprise. May 14th, 1973. America's first space station, Skylab, launches.
Moving up. Skylab has cleared the tower.
Its mission: to prove that humans can live for long periods of time in space, and to expand our view of distant planets and stars. In total, 9 astronauts visit the station. The longest stay is 84 days. But Skylab is plagued with mechanical problems. And in 1974, it is abandoned by its crew and left to await repair. But in 1979, something knocks Skylab out of space. Scientists discover that between 1974 and 79, the sun fires a barrage of solar flares toward Skylab. But it isn't the flares that bring the spacecraft down. It's what follows. Minutes behind each flare is a gigantic wave of radiation. The wave contains huge amounts of electromagnetic energy, X-rays and gamma rays straight from the surface of the sun. The wave travels at the speed of light and smashes into the Earth's upper atmosphere, which heats and expands.
Solar storms, especially solar flares, dump enormous amounts of energy into the upper atmosphere. The upper atmosphere responds by heating up from 500 degrees to 1,500 degrees, and that also causes it to expand out by up to 1,000 miles.
The swollen atmosphere envelops Skylab. The space station is suddenly surrounded by air, where once there was nothing but space. Air drag slows the satellite down, and it begins to fall out of orbit. In July 1979, Skylab crashes to Earth. Luckily, much of Skylab burned up on re-entry. Without regular boosts, thousands of satellites could suffer the same fate as Skylab. The multi-billion-dollar International Space Station is at risk.
Even the International Space Station has to worry about solar storms. It typically loses about 75 yards of altitude every day, and during solar storms, it can lose quite a bit more than that.
But the biggest threat from solar storms isn't to our technology. Radiation can kill. NASA's Neil Zapp is all too aware of the dangers faced by astronauts on all space missions.
Our major problem is that we don't have control over the situation. It's not as easy as turning something off or sending someone home or taking them out of an area. It's very difficult for us to get people out of harm's way once they're in orbit.
No one knows when the next solar storm will strike. And they travel so fast, early warning is next to impossible.
We confirm ignition and the thrusters go.
In 1972, NASA has a close call. In April, Apollo 16 lands on the moon. 8 months later, Apollo 17 touches down.
During the space between these two missions, between Apollo 16 and Apollo 17, there was this large event.
A storm breaks on the surface of the sun. 10 billion tons of radiation rains down on the moon. Unlike the Earth, the moon has no atmosphere to protect humans from the effects of radiation. If the astronauts had been here when the storm struck, they would have absorbed a potentially lethal dose of radiation.
It wasn't by planning, it wasn't intelligent planning that provided for putting the event in the dead space. It was actually a little bit of luck of the draw at that time.
But what happens when a massive solar storm is aimed straight at the Earth? We can't simply move out of the way. For all their power, these bursts of radiation are mere ripples spreading into interplanetary space. The solar storm that hit Quebec is a tsunami. March 13th, 1989. Across the Northern Hemisphere, millions witness a dazzling light show called the Aurora Borealis, the Northern Lights. These sparks are a visible sign of a clash hundreds of miles above the Earth's surface, a war between the sun and the Earth's invisible defense shield, the magnetosphere. Nicola Fox knows the shield like her own backyard.
The sun gives us everything that we need to be able to survive here on Earth, but equally it could take that all away in a split second if we didn't have the magnetosphere to protect us.
The magnetosphere completely envelops the entire planet. This invisible shield flows out from the Earth's core. It punches through the South Pole, cocoons the entire Earth, then plunges back down through the North Pole. Without the magnetosphere, all life on Earth would be vulnerable to high-energy solar radiation. These particles can penetrate living tissue and cause severe damage to cells. When the March 13th radiation cloud collides with the shield, most of the charged particles are deflected safely around the Earth and back out into space. But some radiation does leak in at the poles.
And that really churns up the whole magnetosphere, makes it go to very different configurations than it would normally be in. And in order to redress that balance, because nature always has to be balanced, the aurora are powered.
These mysterious displays of colored lights form when solar particles slam into gases in the atmosphere and cause them to glow. The more powerful the storm, the more dramatic the auroras. This high-altitude battle can cause problems for airliners. At the poles, the atmosphere is especially vulnerable to large bursts of radiation. The wave of energy causes havoc in the upper atmosphere, disrupting GPS systems and blacking out radio signals.
During intense storms, passenger aircraft have to divert to lower altitudes in order to regain communication with air traffic control.
On March 9, 1989, as the radiation from the flare arrives at Earth's upper atmosphere, the battle with the magnetosphere begins. But in Quebec, the power stays on. 4 days later, on March 13th, a second wave of radiation hits the Earth's atmosphere, and the aurora puts on an awesome show. As the northern lights dance in the sky, the lights in Quebec suddenly go out. How does a radiation cloud high in the atmosphere shut down an electricity network on Earth? To find out, NASA develops the OSO-7 satellite. It can aim a battery of UV and X-ray telescopes at the sun. The mission will give scientists their first glimpse of a monster. This white spot might not look impressive, but it's the first image ever captured of the most powerful event in our solar system. It's called a coronal mass ejection, or CME. 10 billion tons of material explodes from the atmosphere of the sun, an enormous eruption. Without Earth's magnetosphere for protection, high-energy particles from the blast could begin to strip away our atmosphere. If a solar flare is the muzzle burst from a gun, then the CME is the bullet. Scientists still don't know exactly why CMEs occur. They're formed from the sun's corona, the atmosphere that surrounds the sun and stretches millions of miles out into space. Temperatures here reach nearly 3 million degrees Fahrenheit, almost 200 times hotter than the surface.
There are magnetic turbulence and magnetic forces lower down in the solar atmosphere that cause literally the outer atmosphere to be blown out into space.
CMEs are an electrified tangle of charged particles and magnetic fields, a superheated bullet of matter from the sun. A CME looks like a solar flare, but it's 100 times more powerful.
Before we knew of CMEs, we thought that the magnetic storms that occurred on Earth were a consequence of this brightening that was seen at the sun, the flare. And as we've learned more about the sun, we've realized that it's the CME that actually causes the magnetic storm.
Roughly half the time a solar flare occurs, a CME follows, but it travels hundreds of times slower.
It is a mass of coronal material that's coming off the sun, and that travels with the solar wind that streams continuously away from the sun at about 1 million miles an hour. So it takes about 93 hours for it to get to Earth.
On March 9th, a solar flare kicks up a wave of radiation from the sun. The wave travels at the speed of light across space. It hits the Earth's atmosphere in just 8 minutes. The coronal mass ejection arrives 4 days later. This is what causes the blackout. Unlike a solar flare, a CME isn't a spray of radiation. It's a barrage.
And all of a sudden, this big addition of 100,000 times as much energy is thrown at the Earth.
The CME creates immense electrical currents in the ionosphere. The upper atmosphere practically crackles with energy. The auroras light up the sky as far south as Texas. Rivers of charged particles flow through the atmosphere and induce powerful electrical fields 60 miles below at the Earth's surface. Suddenly, with no warning, a vast current jumps onto the power grid. The surge races through the system, and the network overloads. The lights go out in Quebec.
We're talking about thousands of components in a power grid that are affected simultaneously, and there really is no place to run and hide from the effects.
The Quebec event was rare, but not unique. So how at risk are we? And when will the next solar storm strike?
For solar storms, it's always a question of when the next one will happen. It's not a question of will they suddenly go away.
To gauge the future threat, scientists need to know how often the Earth has been hit in the past. The hottest storms in the solar system have left their mark in one of the coldest places on Earth, the Arctic Circle. Locked within layers of ice is a history of the Earth. The ice keeps a record of solar storms dating back thousands of years. To see how often the storms hit, researchers look for a chemical they leave behind: nitrate.
You can actually core the ice and measure the nitrate abundances, and you find that the spikes in the abundances match up very nicely with some of the more recent intense storms.
By scanning ice cores, scientists travel back to an age when a massive solar storm struck Earth. A huge peak in nitrate reveals a solar storm that makes the Quebec event look like a firecracker.
The most intense abundance change that we see in the ice core data occurred in September 1859. It was so intense that we call it a superstorm event. It knocked out telegraph service in North America and most of Europe, and it was also seen all the way down in Calcutta, India at the time. It was a major worldwide event seen just about everywhere.
The 1859 storm is the most powerful solar eruption to hit Earth in 500 years. It's 3 times stronger than the storm that blacked out Quebec. If it had hit today, it would probably be catastrophic.
When you think of all of the services that rely on electric power, it's rather staggering to imagine the kind of a geographic footprint that one of these storms would have.
After a superstorm, the lights don't come back on the next day.
Most of the transformers that are used by the big power grids are custom order and can take months to replace.
Imagine months without power. Transportation grinds to a halt. The economy nosedives. No running water. No sanitation. Scarce food. Rampant disease. From the space age to the Stone Age, in the blink of an eye.
A solar storm would affect the power grid in an entire continent because these kinds of storms span the entire planet. It's unlikely that in your lifetime or mine, we're going to see one of these superstorm events. After all, the ice core data was 500 years long, and there was only one of these events in 1859. But there are plenty of events that were a half as strong or even a third as strong. They are more numerous, and because of that, the long-haul effect of these things could be actually substantially worse than one major storm all at once.
It could be worse. The sun isn't the only star that produces solar storms. Astronomers peer far into the depths of space and watch stars being born and others die. A chance discovery shows just how dangerous space can be. Astrophysicist Eric Feigelson is researching deep space, looking for streams of X-rays. But what he stumbles upon blows his mind.
Instead of finding what we thought we would find, we instead found these rapidly changing X-ray sources associated with young stars. And we were quite puzzled, frankly, for some years.
The stars produce mysterious bursts of monstrous X-rays, solar flares out of this world.
So the strongest flares we've seen are 10,000 times stronger in the X-ray band than the strongest flare ever seen in the sun. When we looked at 1,000 young suns simultaneously in the Orion Nebula, we found that they're typically flaring at this level once or twice a week.
Solar storms like the one that hit Quebec can release as much energy as 1 billion atomic bombs. The star's Feigelson studies produce flares 10,000 times more powerful. The Hubble telescope catches an eruption on a star 450 light-years from Earth. This flare is so huge, if it hit a space colony, it would take out more than their power. It would take out their planet. Scientists call it a superflare. It's not just one star that creates superflares. There are regions of space where nearly all the stars are doing it. 1,500 light-years away is the Orion Nebula. It's a brilliant haze of gas and dust. In X-ray, the dust disappears, leaving only the stars. This X-ray movie was filmed over 13 days. Each tiny flash is a flare thousands of times more powerful than any produced by our sun. These stars are just like the sun, except much younger.
This cluster was formed about 1 million years ago. Now, that may sound like a long time ago, but compared to the sun, which is 4.5 billion years old, these are very, very young stars.
The Orion Nebula is where new stars are born.
They'll all become like our sun. They're just like our sun was when it was a young star.
Space scientist Gibor Basri wants to know why young stars create such huge flares.
If you take a given kind of star, say a star like the sun, there's a direct correlation between how much magnetic activity you see on that star and how fast you spin it. The slower the star spins, the less activity it has on it.
Like the sun, these stars create huge amounts of magnetic energy because their equator spins faster than their poles. The faster a star spins, the bigger the arcs, and the stronger the flares. And young stars spin very fast.
Our sun goes around about once a month. When it was very young, it went around every couple of days or a few days. So that's how much it's slowed down. And that means that the sun is now much less active than it was then.
Feigelson describes a sun we wouldn't recognize.
When the sun was a baby star at 1 million years old, it was 3 times bigger. It was a ruddy orange color. It had huge star spots that whipped around every few days, rotating much faster than it is today. And the magnetic fields, which you wouldn't see with your visible eyes, but you'd see with an X-ray telescope. The magnetic fields would be 10 times the size of the star, crackling and seething with explosions.
Some scientists think if it wasn't for the violent early sun, the Earth and all the planets in the solar system might not be here. 4.6 billion years ago, the solar system is just a cloud of gas and dust racing around the young sun. How it transforms into the solar system we see today is still a mystery.
So the disk is full of dust, and it's sort of the consistency of cigarette smoke. These are really tiny dust particles. We're really pretty puzzled about how you get from dust bunnies to asteroids. It's easy to stick snowballs together, but it's not so easy to stick sand balls together.
Basri thinks the violent young sun helps build all the planets in our solar system. Giant solar storms rip through the disk. The dust particles are forced together. Over time, they fuse and grow. The first embryonic planets are born. Eventually, the solar system is formed. And as the sun ages, it begins to slow down. If it hadn't calmed, life in the solar system might never have developed. Yet when the sun coughs, the Earth still shudders. There's little shelter from the effects of a massive solar storm. The only way to protect our electricity network is to shut it down before the storm strikes. But how do you predict a solar tantrum? Solar storms are a serious threat to our high-tech lives in the 21st century. The race is on to predict when and where the next one will strike. In September 2006, Japan launches the Hinode satellite. Its 3-year mission is to map the sun's complex magnetic fields. The information it sends back could prove key to forecasting solar storms. Hinode orbits 370 miles above Earth. Its camera peers straight into the sun's atmosphere. It returns the clearest pictures ever of the sun's surface. In December 2006, Hinode captures this groundbreaking footage. A magnetic arc snaps, and a huge flare erupts. It blasts into the solar system at more than 1 million miles an hour. Carol Shriver uses data from Hinode to generate the first computer model of a solar storm before it erupts. A detailed map of the sun's complex magnetic fields.
What drives these large solar flares is the magnetic field, and specifically its electrical currents running through the magnetic field. So each one of these strands is essentially an electrical current prefabricated in the interior of the sun, breaking through the surface and becoming visible, and then ready to power a flare.
Where the magnetic fields intertwine the closest, the currents are strongest. Shriver replicates these electrical currents in 3 dimensions.
If we tilt this, we can suddenly see that these electrical currents come up from one place, go up by something like 20,000 kilometers above the solar surface, and come down again.
The model shows a red river of energy equal to 1 billion atom bombs. When the flare erupts, it releases that energy in seconds.
The amount of energy that goes off in this flare is simply astounding. It's the equivalent of 1 million times 1 million atomic bombs going off at the same time.
If Hinode can spot these densely packed lines of magnetism before a flare explodes on the sun, scientists might be able to predict when the next solar storm will strike. Until that technology arrives, space weather forecasters use a method of analyzing the sun's activity developed almost 400 years ago. Sunspots. Sunspots form because the sun's atmosphere is hotter than its surface. The magnetic arcs block the atmosphere, making the sunspots burn cooler than the surrounding surface. 6,300 degrees versus 10,000 degrees. Sunspots come and go in an 11-year cycle of maximums and minimums. Solar minimum has few sunspots and the fewest flares. At solar maximum, 200 sunspots or more, all firing magnetic arcs. A week before the Quebec blackout, astronomers identify a group of sunspots on the eastern edge of the sun's surface. The blackout occurs during a solar maximum. The next maximum is around the corner, in 2012. The sunspot cycle tells us the gun is loaded. It doesn't tell us when or where the bullet will strike. Once the magnetic arcs cross, the trigger is pulled and a flare explodes. It reaches Earth in just 8 minutes, too fast for a warning. But the most damaging part of a solar storm is slower. A coronal mass ejection can take up to 4 days to arrive. If we know when the solar surge will hit, we can save the electricity network by shutting it down. At the Space Weather Prediction Center, scientists keep a watchful eye on the sun. They're looking for any increase in activity, including the buildup of sunspots.
Well, the forecaster today is looking at the data, trying to understand what the sun is doing right now, and then making predictions of the effects on Earth.
Solar satellite technology is young. It's observed the solar maximum only 3 times. Space weather forecasting is where Earth weather forecasting was 50 years ago.
If you were trying to predict a hurricane, if you didn't know anything about the speed of the winds and you didn't know anything about the atmospheric pressure at the eye of the storm and some of those types of things, that would be fairly comparable to where we are now in space weather.
You can see a hurricane coming, not a solar storm. Once it leaves the sun's surface, it's practically invisible. It can hold 10 billion tons of matter, but it's spread over millions of square miles. Just a handful of atoms in every cubic foot.
You couldn't see one of these storms arriving at Earth with the naked eye. They are so dilute that they are actually better than the kinds of vacuums that we can create under laboratory conditions.
Satellite instruments are sensitive enough to detect solar storms, but there's a catch. If one heads straight toward us, it's very difficult to tell how fast it's traveling. It's like the batter in a baseball game. As the ball hurtles toward the hitter, it's impossible to judge its exact speed. 3 strikes, and he's out. If scientists misjudge the speed of a solar storm, 1 strike could take us back to the Dark Ages. To help solve this blind spot, in 2006, NASA launches a 2-stage satellite called Stereo.
Stereo's great. We're going to be able to watch coronal mass ejections from perspectives that we've never been able to see before. And most importantly, it would be the one that allows us to watch the event happen along the Sun-Earth line.
After launch, the satellites separate. They use the moon's gravity to reach their orbits, flanking the Earth. The 2 near-identical satellites orbit the sun, but one of them is slightly ahead of the other. They give the first 3-dimensional stereo view of the sun. Scientists can now forecast very quickly if and when a solar storm is going to hit the planet.
It will improve the timing in particular of the forecasts that we would try to make, to mitigate the consequences of that as it went by the Earth.
NASA hopes that Stereo's information will lengthen early warning times from just a few hours to a couple of days. It could prevent blackouts like Quebec from ever happening again. One day, advanced satellite technology might even predict solar storms before they're born.
It won't be next year. It may be a few years, but it's doable now. We've been moving ahead very rapidly with less and less simplifications, with bigger and bigger resolution, more finesse in the models. And we're getting to a state that we can say that we're actually approximating what really happens on the sun.
Stereo could save our way of life from solar storms. For 2 million years, solar storms did us no harm. Less than 2 centuries ago, we harnessed electricity and got our fingers burned. Nobody knows exactly when the next solar storm will strike. Solar maximum is just 3 years away, and once again, Earth could be in the firing line. Hopefully, this time, the lights will stay on.
Imagine a world frozen solid, encased in ice from pole to pole. No life roams these frozen plains. Only glaciers move across them. This is not some distant planet starved of sunlight. According to a radical theory, this was Earth, 650 million years ago. No one knows what triggered this calamitous freeze. But if it happened once, could it happen again? Imagine the most profound ice age you can think of. Temperatures plummet to below zero, even at the equator. Before long, ice encloses our entire planet. Research suggests that this may have happened not once, but 3 times in our planet's past. Welcome to Snowball Earth.
A snowball Earth is certainly the most extreme climate change we can conceive the Earth having ever experienced.
What would happen if the world froze over today? Massive glaciers creep from the poles, crushing everything in their path.
First of all, the Canadians are going to have to dig much deeper holes when they go ice fishing. Next, the governors of Washington, Idaho, Montana, North Dakota, Minnesota, Michigan, and Maine will probably declare federal emergencies.
Cities grind to a halt. Power lines collapse and water supplies freeze. Cars won't start. Roads are cut off by ice. Buildings strain and crumble under deep drifts of snow. Everything is entombed. Our frail bodies struggle to survive.
I think human society would collapse if a snowball Earth happened again.
The oceans freeze over. Fish die and marine ecosystems collapse. Our food supply becomes exhausted. Any surviving humans are trapped in an icy hell.
We would have a mass die-off of humans simply because we could not grow enough food under these conditions.
Incredible though it may seem, the Earth may have frozen over completely. Scientists are finding clues in unexpected places. The story begins with a mystery. In the arid Flinders Ranges in southern Australia, layers of ancient rock hold unusual stones. These stones are foreign to the area. They are known as drop stones. The drop stones are embedded in an ancient sedimentary sea floor that formed around 650 million years ago. Tim Raub, a geologist at the Californian Institute of Technology, hunts for these drop stones at the Flinders Range.
This is an example of a drop stone, a piece of ancient rock that was dropped into the ancient mud on the sea bottom.
These drop stones are visibly different from the sedimentary bedrock around them. Something powerful must have carried them here. But what? Dan Schrag, professor of Earth and Planetary Sciences at Harvard University, believes the answer is glaciers.
We actually have ice cubes here that we've made with pieces of sand and gravel in them. So these ice cubes are like the glaciers that are taking rocks from the land, and then when we put them in the water, they'll actually melt and the sand and gravel will fall to the bottom, just like the drop stones on the ocean floor.
These drop stones are evidence that at some point, this area was covered in a thick layer of ice. But it's difficult to explain how ice could have covered the sun-baked mountains of southern Australia. Unless the continent itself was in a very different place. The continents haven't always been where they are now. They move very slowly across the Earth due to the movement of tectonic plates. 650 million years ago, around the time the Flinders dropstones landed here, the continents were positioned very differently. Since the dropstones formed under ice, perhaps Australia sat nearer to the poles where temperatures were lower. To locate the position of a continent in the distant past, scientists study the magnetic identity of rocks. Certain sedimentary rocks contain magnetic particles. When the rocks form, these iron particles line up with the Earth's magnetic field. Near the poles, they align at right angles to the sedimentary layers. And around the equator, they align parallel to the layers. Even if the rock moves, the distinctive configuration of these magnetic particles remains the same and provides a kind of geological fingerprint of the rock. Professor Joe Kirschvink at Caltech Pasadena is fascinated by magnetism.
Magnetism is magic. I've even named my eldest child after a magnet, so I enjoy magnetism.
Kirschvink and his team analyzed the 650-million-year-old rock surrounding the dropstones. The results were unexpected.
That part of Australia was within 5 degrees of the equator, and it just was the most weird place to expect a glacier.
But Kirschvink had to be sure that this ancient rock still held its original magnetic signature. If the rock heated up after it formed, its native magnetism would have changed. Back at Flinders Range, Kirschvink's team uncovered clearly striped sedimentary rock that provided proof.
Here, tens of thousands of layers of mud grew one at a time, upward and upward, in a glacial lake at the edge of a 635-million-year-old ice sheet.
When this rock formed, layers of sediment built up in distinctive horizontal lines. By comparing the direction of the layers of sediment with the direction of the lines of magnetism, Kirschvink could determine whether the rock's magnetic signature had changed.
We can explain the process of magnetism with a simple eraser. If the rocks formed on the equator and gained their magnetism very early, we would expect the magnetic direction to be parallel to the bedding very precisely like this. And then, since the rocks are soft, if they get squeezed or deformed geologically, you would expect them to rotate like this, and the magnetism would shift with the bedding. On the other hand, if the rock had been squeezed and deformed first, and then gained the line of magnetism like this, we would see them warped relative to the bedding today.
If the rock still had its original magnetic orientation, the lines of magnetism would follow the lines of sediment. But if its orientation had changed, the magnetism would cut through the sedimentary layers. Raub drills into the formation to retrieve solid cores of the rhythmic rocks. Back in the lab, the team analyzes samples of rock using a custom-built hypersensitive magnetometer. This magnetometer measures the orientation of the magnetic particles in the rock. It confirms that the particles were aligned with the rock layers. Kirschvink was astonished.
Quite frankly, when I saw the original study, I didn't believe it. And what in fact we see is that they're like this, and as the rock was warped, magnetism warped. That proves conclusively the magnetism formed before the rock was solidified.
This discovery seems to provide irrefutable evidence that the glacial rocks formed close to the equator. Paul Hoffman, professor of geology at Harvard University, was intrigued.
So if there were glaciers close to the equator where the temperature was warmest, one has to assume that there was also ice in higher latitudes where the temperatures were colder.
650 million years ago, Australia sat near the equator. And yet evidence suggests that its arid rocks lay buried beneath ice. And if there was ice at the equator, there would have been ice all over the globe. These dropstones became the catalyst for a radical theory: Snowball Earth. This is a theory about the most extreme ice age imaginable. And if it happened before, it could happen again. Our world has been through many periods of extreme climate change. But some scientists have proposed that 650 million years ago, the Earth may have frozen over completely. This radical hypothesis raises one crucial question: how could it have happened? Kirschvink proposes that the giant freeze was triggered by the same mechanism that lies behind today's global warming, the greenhouse effect. Except 650 million years ago, it worked in reverse. Greenhouse gases in our atmosphere act like an insulating blanket, trapping the sun's energy to keep Earth's temperatures mild. When the snowball began, scientists suspect that levels of these vital gases fell dramatically.
The Earth's atmosphere might have been filled with methane and carbon dioxide, and the Earth became addicted to this high-level carbon dioxide and methane in order to keep its temperature. Then, if some unknown event crashed the carbon dioxide out of the atmosphere, Earth might have run away into a snowball Earth.
If enough carbon dioxide had been pulled out of the atmosphere, an anti-greenhouse effect would have plunged the Earth into a deep freeze. But this theory is only possible if there's a mechanism that could pull all the CO2 out of the air. In fact, carbon dioxide is removed all the time through a process called silicate weathering.
Weathering is a geological term for the decomposition of rocks under the influence of the weather. It's a process that converts solid rock into soil. Now, its importance for the climate is that weathering consumes carbon dioxide, which is a major greenhouse gas in the atmosphere.
Carbon dioxide reacts with water vapor in the atmosphere to form carbonic acid rain. This acidic rain weathers limestone on land and carries away the eroded sediment to the sea. Here it builds up, eventually forming limestone on the sea floor.
So the presence of the limestone is the evidence that weathering is occurring.
The more carbon dioxide gets locked away in limestone, the cooler the Earth becomes. But if this is happening all the time, something must have amplified the process for the whole world to have frozen over. Again, clues lie in the position of the continents. The movement of tectonic plates continually shifts the continents around the globe. Today, a lot of the continents are located in higher latitudes. If the Earth cools, the continents near the poles ice over. The ice prevents the rocks beneath from being weathered by carbonic acid rain. This means that the weathering cycle is kept in balance. With less carbon dioxide locked away in limestone rock and more in the atmosphere, the planet warms. Scientists have worked out that 650 million years ago, the continents were clustered around the equator, where it's warm and wet. Consequently, the global rate of weathering would have been higher.
During the snowball Earth, we suspect that there were many more continents at the equator, and this would actually lead to a situation that would make the planet vulnerable to a global glaciation.
As the Earth cooled, ice formed at the poles, but because there were no continents in the higher latitudes, ice accumulated on sea rather than on land. There was nothing to regulate the weathering. The cooling continued unchecked, and the world got colder and colder. This runaway scenario is certainly plausible. But although extreme weathering could be behind an ice age, it doesn't explain how the Earth could have iced over completely. Geologist Galen Halvorson from Adelaide University studies triggers of the snowball.
One of the hardest parts about understanding the snowball is really how it began. We think that it must have began like a normal glaciation.
Normally, living things help to regulate the Earth's climate by maintaining the delicate balance of carbon dioxide. Plants consume carbon dioxide. Animals produce it. These consumers and producers help to regulate the climate, ensuring the Earth is neither too hot nor too cold. If there's more carbon dioxide in the atmosphere, it gets warmer. This causes plants to grow faster, which in turn draws out more CO2 from the air.
So that is a feedback against it getting too warm. And in reverse, if it starts getting too cold, then the biosphere responds by not drawing down as much CO2, and that allows CO2 to go back up. So there's a sort of buffer in the form of life on Earth that prevents temperatures from getting too cold or from getting too hot.
But rewind 650 million years and witness a very different story. Life on land was in its early stages of evolution. Most living things were in the oceans. This half-formed biosphere could not prevent the Earth from swinging to wild extremes of temperature. Colonies of single-celled organisms called cyanobacteria were the first to photosynthesize. They pulled carbon dioxide from the surrounding water to precipitate calcium carbonate, and they used this to make dome-like structures of rock. Geologist Jim Gehling is an expert on these early life forms.
Temperatures were dropping at this time, 650 million years ago, for the very good reason that carbon dioxide, the principal greenhouse gas, was being taken out of the atmosphere and locked away on the seafloor.
This trapped carbon dioxide can still be seen today in stromatolite reefs.
This is actually solid carbon dioxide, and I can release that carbon dioxide after all those hundreds of millions of years when I put this weak acid on the rock. And there you see it erupt as white bubbles of carbon dioxide spring out of the rock, go back into the atmosphere to take up their role all over again as greenhouse gases.
The more carbon dioxide the cyanobacteria locked away, the cooler Earth became. Our planet was hurtling towards a deep freeze that would last for millions of years. $650 million years ago, the Earth's temperature plummeted. Huge sheets of ice spread across the planet. Eventually, they engulfed most of the land and sea. This was no regular ice age. Ice ages are nothing out of the ordinary. We experience them every 100,000 years or so. They are mainly caused by small changes in the Earth's orbit, which alter its position relative to the Sun. When our planet receives less of the sun's energy over a number of years, ice forms high in the northern hemisphere and advances down. At the height of the last ice age 21,000 years ago, these icy sheets reached down as far as New York. But the tropics stayed warm. Only about 30% of our planet froze. But 650 million years ago, some scientists believe the ice kept coming, until eventually, most of the globe was covered. What could have caused this runaway cooling? The answer must lie in how our planet keeps or loses the sun's energy. The Earth's surface is made up of land, open ocean, and ice. These all reflect sunlight to a different degree. The amount of light a surface reflects is known as its albedo. Deep dark ocean has a low albedo, since it absorbs a lot of sunlight. White snow and ice have a very high albedo, since they reflect more of the sun's energy back into space. Tim Raub demonstrates how dark and light colors heat up under the sun.
The temperature of a white car sitting in the sun is only 120 degrees. The temperature of a black car sitting in the sun is 144 degrees. The black car absorbed light, the white car reflected it.
White reflects more sunlight, keeping whatever it's covering cooler. The more ice that covers the Earth, the more of the sun's energy reflects back into space and the colder the planet becomes. This cooling leads to more ice forming, which further increases the surface albedo. This is known as ice albedo feedback. And something may have accelerated this cycle of cooling even more. New research suggests that when seawater freezes at very low temperatures, its composition changes and it can become more reflective. At the University of Washington's Polar Science Center, Bonnie Light studies the relationship between ice and light. In the cold room, she freezes buckets of salt water at different temperatures. One of the buckets is exposed to snowball Earth temperatures of -10 degrees. The surface of this ice becomes much whiter.
Okay, so this bucket contains seawater that was frozen in a cold room at 5 degrees above 0 Fahrenheit. And we consider this a good laboratory analog for modern day sea ice on planet Earth. And you can see that the surface of it is kind of gray colored, dull appearance. And this bucket also has salt water in it, although this salt water was frozen at about 10 degrees below 0 Fahrenheit. And we consider the ice in this bucket to be a good analog for sea ice on snowball Earth because it's very cold.
At snowball Earth temperatures, the composition of sea ice changes, turning its surface from gray to bright white.
And you can see that these crystals in this case have started to collect at the surface of this cold ice. And so I can kind of scratch away these crystals, and you can see that this is basically just a deposit on the surface of this cold ice.
At -10 degrees, salt molecules in the ice begin to form tiny crystals.
If you can isolate them under the microscope, they look like little gemstones. They're really quite beautiful.
These bright crystals have a dramatic effect on albedo. The white surface scatters more of the sun's energy and reflects it back to the atmosphere, causing temperatures to drop even further. In the 1960s, Soviet climate modeler Mikhail Budiko demonstrated how runaway ice albedo could cause a cooling Earth to freeze completely. Like many of his contemporaries, Budiko was worried about the effects of a nuclear winter. Nuclear explosions create clouds of smoke and dust, which block the sun's energy and lower the Earth's temperature. Budiko developed a mathematical model to work out the odds of a global ice age. He showed that if the Earth's climate cooled enough for ice to form in the lower latitudes, then the ice albedo would rise at a faster rate. And once the glaciers reached a certain latitude, the Earth would tip into a snowball-like state.
Somehow or the other, the ice line, the glaciers, reach some critical latitude, around 30 degrees. And once they hit that latitude, very, very rapidly, the Earth would have been entombed in ice.
Bedico's groundbreaking work showed how this snowballing effect could create a totally frozen planet within just a few decades.
Bedico's work was extremely important in demonstrating that it was possible that Earth might slip into a climate catastrophe which was covered completely with ice. It had not been recognized as a possibility before that.
If the Earth became entirely covered in ice, nearly all the heat it received from the sun would be reflected back into space. The planet would become locked in ice. So if runaway freezing trapped the Earth in ice, how did it ever escape? Some scientists suggest that 650 million years ago, our entire planet was locked in an extreme ice age. It was a unique event, the result of a set of improbable triggers. Or so they thought. Then, in 1997, evidence emerged that it could have happened more than once. It came from glacial deposits in South Africa that were over 2 billion years old. Paleomagnetic evidence suggests that these formed near to the equator. Geologist Paul Hoffman believes this could be proof that the Earth froze over completely at least twice in its history.
The best evidence for a snowball Earth 2.22 billion years ago is paleomagnetic evidence from South Africa. There are glacial tills there, boulder clays, that formed very close to the equator.
This discovery raised the possibility that the snowball wasn't a single event, but a recurring condition. Scientists raced to find the trigger for this earlier deep freeze. The cooling appeared to coincide with the Great Oxidation Event. Deep in the ocean, some of the oldest organisms on Earth evolved a mechanism called photosynthesis. The ability to convert carbon dioxide into oxygen using the sun's energy. As these photosynthesizing microbes thrived, they had a profound effect on the Earth's climate. 2 billion years ago, our sun was weaker. Our planet relied on greenhouse gases like carbon dioxide and methane to maintain its temperate climate. But photosynthesis uses up carbon dioxide. It also produces oxygen, which destroys methane. The result, a double whammy. Levels of both these vital greenhouse gases plummeted.
You have a precarious situation. You have a planet that's greenhouse needs methane, and you suddenly evolve a bug that destroys the methane.
Maybe the first bacteria that photosynthesized crashed the carbon dioxide and methane from the atmosphere and triggered the first snowball Earth.
As oxygen production soared, methane levels tumbled. With the loss of that greenhouse gas, the Earth spiraled into a deep freeze.
It's kind of a frightening conclusion that a single-celled mutant bug destroyed an entire planetary ecosystem. Destroyed it, turned it into a snowball for maybe 35 to 100 million years.
Some scientists now think that our planet has been encased in ice on at least 3 separate occasions, and each time under different circumstances. But these snowball Earth scenarios present a huge problem. If our planet was trapped in ice, how did it ever escape? Something must have caused a global meltdown. Evidence of the thaw is right here. On top of the dropstones sit layers of a peculiar reddish-gray rock. These layers stretch for miles in the Flinders Range, Death Valley, and almost everywhere where the glacial rocks appear. These are carbonate rocks, which form in warm, shallow seas. But here, they appear right on top of the glacial deposits.
So here's a sample that actually shows the end of the snowball event. So that's an ice-rafted stone dropped out of an iceberg. And these are little grains that also fell out of an iceberg. And immediately on top of that, without any break in sedimentation, is cap carbonate that's precipitating directly out of the ocean and accumulating on the seafloor. And exactly the same relationship is seen all over the world.
Their presence is evidence of a sudden and drastic temperature increase. Only one thing could have triggered this: a huge injection of greenhouse gases such as carbon dioxide. In order to melt snowball Earth, concentrations of carbon dioxide had to be around 350 times higher than they are today. But if the whole planet was encased in a thick layer of ice, where did the carbon dioxide come from? Caltech professor Joe Kirschvink had a revelation.
I woke up in the middle of the night and said, that's got to be it. It just dawned on me that these subaerial volcanoes, like in the Aleutians and the Yellowstone, these volcanoes sit and they spew CO2 into the air.
Even beneath the ice, volcanoes would have continued to release immense volumes of carbon dioxide. With the rest of the planet still ice-locked, there would have been no mechanism to remove it from the atmosphere. Over millions of years, levels of this greenhouse gas would have built up, eventually producing enough warming to offset the ice albedo. The ice melted, sending global temperatures spiraling upwards. As this melted ice water evaporated, it swelled the atmosphere with moisture, creating torrential rainfall. Carbon dioxide in the atmosphere acidified the rain. Acidic downpours rapidly eroded limestone, washing sediment down into the oceans. Here, layers of carbonate sediment accumulated on the sea floor to become carbonate rock. Dan Schrag demonstrates what could have happened.
Instead of carbonic acid from carbon dioxide, we're going to use a little stronger acid to make it go a little faster. This is nitric acid, and when we add it to the limestone, it will dissolve away the limestone and ultimately create a very clear solution. So you can see it bubbling away. And when this is added to the ocean, it reacts and creates the cap carbonates that blanket the top of the glacial deposits.
But still, not everybody is convinced that the planet was ever entirely covered in ice. Some scientists argue that the chances of life surviving a full-on snowball are virtually nil. Above the ice, the freezing conditions were too hostile, while below it, life was cut off from sunlight. Yet there is evidence that photosynthesizing organisms did survive the freeze. Single-celled cyanobacteria existed right the way through. Cyanobacteria can survive extremes of temperatures many degrees above and below zero. But if the oceans froze over, a thick layer of ice would have sealed them away from the sunlight. With their energy source blocked, they would have died out.
If you'd been diving on a tropical reef before snowball, this is what you would have seen. Slime world, mounds of slime on the sea floor. And if you touch them, you'd find out that they're actually rock. A surface covered with slimy material, which is actually cyanobacteria. the earliest, the most primitive form of life that's been around for 3 billion years up until this point and is still around today.
Critics argue that nothing could have survived the ferocious conditions of a total global freeze. They maintain Snowball Earth was nothing more than a severe ice age with extensive glaciers and a belt of open water around the equator. Philip Allen, a geologist at Imperial College London, believes that the evidence for a frozen planet is flawed.
I am not in agreement with this Snowball Earth hypothesis. The major hole in the theory, as far as I'm concerned, is that the sedimentary rocks deposited during the glacial periods do not support the idea of a long-term global freeze.
Philip Allen's counter-evidence includes the ripple-like patterns in rocks formed 650 million years ago.
When you look at those sedimentary rocks, it indicates open water. The wind was able to blow over the water surface and form ripples, wave ripples on the seabed. So they are really conclusive proof of an open water surface rather than an ice-covered one.
Waves in an open sea left imprints in the sediment of the sea floor. When the water disappeared and the sediment turned into rock, the ripples remained. Allen and others propose an alternative to the Snowball Earth. It's known as the slush ball. In their version of events, the Earth never froze completely. Some patches of open land and sea remained. But proponents of the snowball theory don't suggest that the frozen planet was without any open water. Schrag believes that life could have survived in ice holes around sources of geothermal energy.
Even in a completely ice-covered planet, there's still plenty of places where there are hot springs, geothermal heat from volcanoes, probably thousands and thousands of such little holes. And in many of those little holes, you could sustain life throughout the Snowball Earth period.
The reality is, we may never know if the world was ever completely frozen over.
Sometimes people think of the Snowball Earth like a cartoon, an oversimplified planet. But the real world is much more complicated than that.
Whether slush ball or snowball, everyone agrees there was a profound global freeze. And when our world emerged, 635 million years ago, something unexpected appeared. Life. Far more complex than anything that had gone before. After the big freeze, life on Earth exploded. Our planet, 650 million years ago. Temperatures plummeted, turning our planet into a hostile place. Yet somehow, life survived. And as soon as the frozen Earth began to thaw, it blossomed. And there was an unprecedented explosion of life on Earth. Before the deep freeze, life was primitive. Single-celled organisms and algae were mostly confined to the oceans. Shortly after it ended, the first multicellular animals appeared. The big question is, did the global cooling trigger this great leap in evolution?
Well, the best evidence is the coincidence in timing. The fact that the first fossils of multicellular animals occur less than 3 million years after the last snowball termination.
Shuhai Xiao is a geologist at Virginia Tech. He unearthed some of the oldest multicellular animal fossils in the world in a mine in southern China.
The fossils are really small. They're about ½ millimeter in diameter, so you can barely see them with naked eyes.
Under a microscope, he discovers that the fossils are very primitive animal embryos. Some fossils show clusters of 2, 4, 8, and more cells.
It was really exciting when we found those. Those are some of the earliest animal fossils, and they have found in rocks that were deposited almost immediately after the snowball Earth ended.
Fossils of these animal embryos date back to just 3 million years after the global freeze ended. That might seem a long time in human terms, but geologically, it's the blink of an eye. Over the next 80 million years, animal life exploded. In the Flinders Ranges in southern Australia, geologists have found some of the oldest fossil evidence of complex multicellular life. These creatures bear little resemblance to life today, but they offer clues to the genesis of early life. 650 million years ago, this area was beneath a shallow sea. Bizarre, soft-bodied organisms similar to jellyfish or flatworms lived on the sea floor. Some of the organisms got trapped in fine silt of tidal flows where they fossilized. Jim Gehling has been investigating these early animals.
Probably our ancestors lie in these rocks. This thing here, Dickinsonia, can best be described as some kind of a pancake or mat-like worm creature. It doesn't have a proper head, it has what appears to be a gut, very fine segments.
But this doesn't explain how the severe planetary freeze could have triggered a leap in evolution. What we do know is that there is a striking coincidence between the rise of oxygen and the end of the snowball. Oxygen levels rise following these global ice ages because of a chemical reaction between ice and sunlight. 650 million years ago, there was no ozone to stop the sun's ultraviolet light hitting the Earth's icy surface. This UV light reacted with water vapor to form hydrogen peroxide. The hydrogen peroxide remained in the ice for millions of years. But when the ice melted, the hydrogen escaped, and the peroxide converted into water and oxygen. Oxygen reached the same level as we have today. At roughly the same time, the first complex animals appeared. More oxygen enabled life to become multicellular. A single cell can take up gases and oxygen from water. Oxygen fuses across the cell membrane into the cell. However, when several cells link together, it's harder for oxygen to diffuse from one cell to the next. The pressure of oxygen needs to be higher.
You need to have a high enough pressure of oxygen to have a circulatory system bring the oxygen all around the body. After the last snowball Earth, oxygen seems finally to have been high enough to support hundreds, thousands, millions of small, early animals on the seafloor.
Oxygen turned out to be the linchpin of evolution. The ability to use oxygen enabled life to become dramatically more diverse.
Oxygen gives us 20 times more energy, or more than 20 times more energy, than any other thing that we can breathe, or that life can breathe. You can have bigger animals, you can have more active organisms, you can have plants that grow and transport liquids from roots to the leaves, and you can have birds energetic enough to fly. Without oxygen, we would all be slime.
A frozen Earth may have given early life a push forward. But if the world were to freeze over again, we'd struggle to survive. We know it's happened several times before. The question is, could it happen again? One factor in our favor is the sun. Over the last 4.8 billion years, it has been getting more and more active as nuclear fusion generates more and more heat. The sun today is about 6% warmer than 650 million years ago. So in the short term, another deep freeze is unlikely.
The sun is warmer today. That probably helps us out. But until scientists really understand what causes snowball Earths, I don't think any of us know whether we're in danger or not of a recurrence.
But there is one possibility that could result in another global freeze: a shift in the position of the continents. We know their arrangement influences the climate. If the majority of the continents were clustered on or near the equator, the Earth would be more likely to turn into a snowball. Cooling temperatures would cause ice to form in the open ocean of the poles, while weathering would continue on the continents. With more and more carbon locked away, temperatures would plummet.
If all the continents were near the equator, then the Earth could get colder and colder and sea ice could form and get to lower and lower latitudes, closer and closer to the equator.
Today, our world seems safe. Most of the continents are near the poles. But plate movement never stops. At some point, millions of years in the future, the continents may group around the equator once again.
I think it's possible someday, if the continents were in a very different position, maybe hundreds of millions of years from now, that we could indeed have another snowball Earth.
It's unlikely that mankind will be around to witness another snowball Earth. But the Earth will still be here. And just like it has in the past, our planet will survive and enter a new phase in its extraordinary history. In the empty blackness of space, surrounded by hostile planets and freezing vacuum, planet Earth is an oasis of life. And all because of our protective cocoon of gas. This blanket of air shapes everything we see on Earth. It protects, insulates, and sustains us. It carries water around the globe and shields us from cosmic impacts and killer radiation. It's time to uncover the invisible wonder that is our atmosphere. Down here on the Earth, we rarely give much thought to our atmosphere. Because we can't see, smell, taste, or hear it, we take it for granted. But our air is all that stands between us and the vacuum of space.
We've got this canopy that provides us a lot more than just an atmosphere to breathe in. It definitely shields us.
The atmosphere is divided into 5 distinctive layers: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each layer is less dense than the one below, stretching miles above our heads.
How far out it goes is depending on which scientist you talk to. Some say it ends at 300 miles, some say it extends out to Mars.
We live in the layer closest to the ground. Here in the troposphere, the air is thickest and the pressure greatest. Our bodies are perfectly matched to these conditions.
Our chemistry, our very nature, our metabolism is completely shaped by the atmosphere.
To appreciate our atmosphere, we'll rise through its layers, traveling from the planet's surface, miles up above the mountains and the clouds, to the very edge of space. August 16th, 1960. One man is preparing for a record-breaking journey into the mysterious skies above. To a lethal world above 99% of the Earth's air, where an unprotected human would die in seconds. Where the temperatures plunge to 67 below, and the air pressure is 100th of that at the surface. Colonel Joseph Kittinger will travel almost 20 miles high. And then he will jump. This is a key military mission, one of the first steps in the space race. Kittinger will be testing the human body's resistance to high altitude, low pressure, and rapid free fall. He will be trialing new technology he hopes will protect him.
It had never been done before, but we were not there to set a record. We were there to gather information that we needed for our space program and for our high-flying aviators.
Ground crew prepares his vehicle, a helium balloon, and a rudimentary open-sided gondola.
Just an open gondola. It was designed just to carry me up there. It was a space platform, an elevator, I called it.
At 5:30, Kittinger's preparations are over. He boards the gondola.
My crew chief said, "Are you ready?" I said, "I'm ready, let's go." It was a very smooth takeoff, and I started ascending. Up, up, up.
30 minutes after takeoff, Kittinger reaches 29,000 feet, the middle of the troposphere. At this altitude, the air is so thin that each breath contains only a third of the oxygen found at sea level. Kittinger breathes from gas bottles connected to his sealed helmet. He's still barely a third of the way to the jump point. There are another 14 miles to go, and the air pressure is dropping rapidly.
So at about 40,000 feet, suddenly the pressure suit starts inflating, and that's when you start checking it to make certain that it's working properly.
But there is a crucial fault in the suit. The glove covering his right hand is not sealed.
I had an option to tell the ground that I had the problem, and I knew that if I did, they'd probably make me abort the flight. And I was concerned that if we had to abort that flight, that we would have been turned down to try to do it again. So I didn't tell them.
Kittinger prays that this is an isolated fault and continues to climb at 1,000 feet per minute. After 89 minutes, he approaches his target altitude. The balloon's climb slows and then stalls. Kittinger is in the mid-stratosphere, a record 102,800 feet high. And it is now time to make the long, swift journey down.
When it came time for me to jump, I was ready to jump because I was heading back toward a more friendly environment, a friendly planet that we're used to. I had made this jump 1,000 times in my mind. I'd gone through every step 1,000 times. Well, just before I jumped, I said a silent prayer. I reached over and hit a button that started the cameras going. And then I just did a little hop off the step of the gondola. You can't tell that you're going fast, you can't tell anything. And I looked up at the balloon, and the balloon was firing into space. And I said, gosh, that's amazing. And then I realized it was me that was going down at a fantastic rate, and the balloon was standing still.
He falls for 16 miles. The thin air offers almost no resistance. He reaches 614 miles an hour, approaching the speed of sound. After a record-breaking 4 minutes and 36 seconds of freefall, Kittinger opens the main parachute. He drifts down to the desert floor and lands.
We were just elated because we had accomplished what we set out to do. There was a lot of people who said we couldn't do it, and we proved that we could do it.
The mission has been a stunning success. Kittinger's skydiving record stands to this day. He takes his first deep breath of air with a newfound appreciation for our atmosphere.
It was a relief to be back on the planet Earth that we love so much, a planet that has an atmosphere that we can live daily.
Kittinger forged a dizzying path through the atmosphere. Our journey begins just a few feet off the ground with the air we breathe. We take for granted Earth's blend of gases, the perfect mix for heat and energy. And astronomer David Grinspoon believes we'd be hard-pressed to find its equal anywhere.
The more we learn about planets, the more we learn that they're all individuals. They're like people in that sense. So as far as what we know now, Earth's atmosphere is completely unique.
In the past century, telescopes and space probes have uncovered the extreme atmospheres of our neighboring planets. A journey across our solar system reveals exactly how unusual Earth is. Clouds of near-frozen gas flow over the icy surfaces of Uranus and Neptune, while the sun has blasted away the atmospheres of Mars and Mercury.
To me, it seems as though Mercury doesn't have an atmosphere at all. But in fact, if you were on the surface of Mercury, it would look to you as if you were out in outer space.
In contrast, Jupiter and Saturn are all atmosphere.
Unlike Earth, Jupiter doesn't really have a solid surface that you could stand on and then have your head up in the atmosphere looking at the clouds. It's just a giant gas ball.
Only one other planet shares the Earth's thick atmosphere and rocky surface: our near neighbor, Venus. But even here, there are striking differences. Dr. David Crisp has spent 20 years studying Venus's acrid air.
Imagine you're at the surface of the planet Venus. You're at pressures that are high enough to crush a nuclear submarine. The pressures there are about 90 times the pressure of the Earth's surface.
This pressure is combined with extreme heat, 900 degrees Fahrenheit, hot enough to melt lead. Clouds drift over the baked surface, but they are not water vapor. Venus's clouds are made of concentrated sulfuric acid. Venus is a stark example of how extreme an atmosphere can be. But the real mystery isn't why Venus is so hostile, but why Earth hasn't followed the same path.
As planets go, Earth and Venus are essentially twins. They're almost exactly the same size. They're also very close together in the solar system. In spite of that, their environments evolved in dramatically different ways.
To discover why these twin planets followed separate paths, and to explore what gave us our precious atmosphere, we have to travel back. Back 4.5 billion years to the birth of the solar system itself. The birth of the solar system created Earth's earliest atmosphere. Huge quantities of material orbiting the sun fused together into protoplanets. Jupiter and Saturn formed into gassy spheres. But on Earth, most of the material condensed into a molten core. The remaining gases bubbled forth from the liquid rock, forming the first atmosphere. Our planet's gravity stopped these gases from drifting off into space. But Earth now had to face the ravages of the solar wind, a stream of charged particles thrown out by the sun. This same wind had a catastrophic effect on Mars. It has stripped the air from the planet's surface, blasting it deep into space. The red planet's atmosphere is now only 1/100th as thick as Earth's. Our planet was spared this fate. The magnetic field generated by the Earth's core blocked the solar wind, preventing it from blasting away the fragile air. But the Earth's atmosphere was still very different from the one we breathe today. It contained high levels of carbon dioxide, a gas with a key ability to absorb and hold on to heat. Carbon dioxide still makes up 95% of Venus's atmosphere. It superheated our twin planet to the point where its water boiled away into space. And yet, this didn't happen on Earth. David Crisp believes that was down to a chance event.
If Earth kept all of its initial atmosphere, it probably would have turned out a lot more like Venus. But that didn't happen. We were the victims of a very lucky accident.
Earth's big break came 4.5 billion years ago. Back then, the solar system wasn't limited to the 8 planets it has today. Instead, a swarm of protoplanets, or planetesimals, orbited the sun like bees around a honeypot. One Mars-sized body was heading straight for Earth. In a colossal cosmic collision, it slammed into our planet, creating our moon, and according to Crisp, removing the atmosphere that still blights Venus. This ancient event was the defining moment for our atmosphere. With the original deadly gas mix blasted away, our planet's air could slowly evolve into what it is today.
We were left with this atmosphere made of molten rock and vaporous rock. It took millions of years for that atmosphere to fall out and to be replaced by an atmosphere made up of nitrogen and carbon dioxide and water vapor.
These new gases came from above and below. Volcanic eruptions spewed out fresh stalks of nitrogen and carbon dioxide from within the planet's molten core. While the vital element of water may have been delivered by icy comets, each impact bringing a new supply of frozen liquid. But the air still lacked one of its key ingredients.
One of the things that was missing is free oxygen, molecular oxygen, O2, the stuff we breathe.
Dr. Janet Seifert of Rice University in Texas searches for the event that produced the atmosphere's final element.
We know from the rock record that for the first half of Earth's life, there was no oxygen in the atmosphere whatsoever. There were greenhouse gases like methane and CO2, but there was no oxygen.
But the rock record shows a sudden change, dated to around 2.5 billion years ago. Evidence of the first oxygen in the atmosphere. The gas was released by a humble microscopic living organism called cyanobacteria.
Well, it turns out cyanobacteria are the only things that can actually produce oxygen. So we know that at some point cyanobacteria colonized enough of the planet in order to produce enough oxygen that it became resident in the atmosphere.
As the microbes multiplied and spread, the gas built up in the air, transforming the planet in a process known as the Great Oxidation Event.
Oxygen is very powerful. The world gets turned upside down. Everything has to begin to adapt to now a completely new atmosphere where oxygen is dominating.
First, the oxygen reacted with the oceans, causing iron within them to form rusty deposits on the sea floor. Then its effects reached dry land. It reacted with soil and rock, giving them a reddish, rusty tinge. And once these minerals had absorbed their fill of oxygen, the gas began to gather in the atmosphere, with dramatic consequences for life.
Complex animals could have much higher metabolisms because of the sheer potential that oxygen provided for them, and a whole different kind of evolution was able to take place.
Powered by oxygen, life evolved from single-celled organisms to complex animals. And plants also began releasing oxygen, thanks to an ancient adoption of photosynthesis.
A very ancestral, primitive plant cell either engulfed or tried to digest or surrounded a cyanobacterium. And instead of digesting it, it actually became an organ within the plant. So every bit of the oxygen, even if it's coming from a plant that you see in your yard, is coming from an ancestor of a cyanobacteria resident inside the plant.
With the rise of oxygen, the air's unique blend of gases was complete. This air we breathe has changed planet Earth, molding its terrain and habitats. And as we continue our upward journey, we run into another vital substance, water. The turbulent movement of our atmosphere carries water vapor around the globe. Powerful winds and violent storms smash our buildings and drown our fields. But without them, the land would be bone dry. Our atmosphere is in constant motion. The moving air that causes our weather circulates between the ground and 50,000 feet. It is the sun that drives this movement. When solar energy reaches Earth, it heats the surface and atmosphere, but it does so unevenly. This temperature difference causes the air to move. Hot air near the equator expands and rises. Cold air at the poles becomes denser and sinks. NOAA's Marty Ralph can track its movement over the globe on the revolutionary Science on a Sphere simulator.
What we're seeing here is a portrayal of the Earth's surface temperature, and red and warm colors are warm temperatures like we see in the tropics here. Up in the poles, you see the blues and the greens. Those are the colder surface temperatures. So we can watch this and actually see the warm air moving northward, the cold air moving southward, and we can see the changes in the seasons.
If the atmosphere didn't move, the poles would be 45 degrees cooler and the equator 25 degrees warmer. The great deserts of the Sahara, Atacama, and Mojave would expand dramatically. Northerly cities like London or Boston would be locked in an icy winter. It is only the atmosphere's circulation that prevents this. It regulates the temperature, moving the air to create the weather that covers our globe. The planet's rotation twists the air as it flows, helping form the hurricanes that lash the coasts. As moist air wells upwards, clouds become electrically charged and send lightning bolts crashing down to Earth, superheating the air to 18,000 degrees. And as the air cools, water vapor condenses into clouds and rain. This water evaporates from the world's oceans. At any moment, 0.001% of the world's water is being carried in the air. But that tiny percentage adds up to almost 3,000 cubic miles of liquid. If the air didn't carry water, the land would be bone dry.
Storms do a really important job for the atmosphere. They help reduce the difference in temperature between the poles and the equators. And in the process, they actually create the rain and snow that we depend on.
One of the most powerful weather systems is a newly discovered set of water channels running through the air. Ralph's current research focuses on these mysterious rivers in the sky.
One of the phenomena that really influences where the water is available for us are these regions where water vapor transport is focused. We've come to recognize that phenomena as an atmospheric river.
Atmospheric rivers are narrow channels of hurricane-force winds that can stretch for thousands of miles. A single river can carry 3 times as much water as the entire Mississippi. They provide almost half the annual rainfall for parts of the American Pacific coast, but when they remain over one area for a day or more, they can produce violent flooding.
Heavy winds, lots of water vapor, a storm track that's not moving fast, adds up to a big flood event.
The rivers were only recently discovered because they form over the world's oceans. We still don't have enough data to forecast their floods.
An example of the challenges we face in weather prediction is that while this model can actually produce an atmospheric river, like we're seeing right here, a week ago today we looked at the forecast for today, and it said there should be a strong atmospheric river creating heavy rain in Northern California. Well, instead, it's hitting Canada. That's a huge difference.
To fill the gap in data, Ralph explores the rivers on research flights. The rivers form in front of banks of cold air. They create channels of wind that carry huge quantities of water vapor from the ocean to the coast at up to 100 miles an hour.
These are like conveyor belts for water vapor. They're very narrow, and yet they do 90% of the water vapor transport for the global atmosphere at those latitudes.
When the airflow hits a mountain, it rises up, shedding its water as rain and snow. Ralph has tracked how the rivers move with the changing seasons. But to fully forecast the floods, he needs a lot more atmospheric data. He believes robotic drone aircraft, developed for the military, could continually measure the air over the oceans, charting its temperature, winds, and humidity. And the flights could also track how the rivers are changing.
We're starting to see evidence that the more intense atmospheric rivers might become more frequent in certain parts of the world, and that will contribute to increasing the frequency of flooding.
The changes Ralph has identified are part of a wholesale shift in our climate and atmosphere. Deserts are expanding, while rainforests are drying out, all due to a change in the chemical makeup of the air. This blend has always been in flux. We alter the proportions with each breath we take. But our factories and homes, planes and cars, amplify the process. For over 2 centuries, we have been dramatically increasing the amount of warming carbon dioxide in the atmosphere. So far, the planet's natural air filters have pulled nearly 55% of it out of the air.
The North Atlantic has absorbed a tremendous amount of carbon dioxide, but at the moment it's almost completely saturated by carbon dioxide, so it's not absorbing very much more. It's almost like a bottle of some kind of soda pop. If you warm it up a little bit, it'll actually fizz and release CO2.
As these natural safety valves close, we will face an even more dramatic rise in temperatures. The global average could be up 7 degrees Fahrenheit by the end of the century, wreaking havoc with weather patterns and habitats. We can prevent climate change by preserving the air's delicate blend of gases, the unique mix that sets Earth apart. And our planet is also marked by how this blend sits above the surface in a distinct layered structure. As we rise above the clouds and winds of lower altitudes, we enter a completely new zone. A world of extreme temperatures and ever-thinning air. Air that would kill us in seconds, but which shields us from deadly radiation. We live in a tiny sliver of Earth's atmosphere called the troposphere. Winds and clouds, rain and snow dominate this turbulent zone, but above it lie miles of freezing dry air. The conditions there would kill a human in seconds, but we desperately need the high atmosphere's weight and protection. Engineer John Powell's balloon team has spent 27 years exploring its layers, pushing further and further into this remote, dangerous world.
Sometimes we just run into a phenomenon that we have no idea what that was. We just have this moment of data in it that we need to go back and explore. But it really is like a completely alien, foreign world up there.
The team has made over 90 launches. Each one edges them closer to their ultimate goal of reaching space.
You can use balloons not just to go to the edge of space like we do now, but go all the way over the line and actually use balloons or airships to go all the way into space. Space travel without the rocket.
Officially, the atmosphere ends and space begins 62 miles up. This sounds high, but on a tabletop globe, that would only be as thick as the coat of varnish. And in reality, the air extends out much farther. The atmosphere's lowest layer, the troposphere we live in, ends 40,000 feet up. the cruising altitude of airliners. Above are another 4 distinct layers.
They're all separated by their temperature. It gets colder and colder and colder, then it warms up to a nice toasty 0. And then it starts to get colder again. So whenever the temperature changes directions, you know you've made it into another layer.
First comes the stratosphere, a stable layer without strong winds. Then temperatures in the mesosphere plunge to -150 degrees Fahrenheit. Above that is the thermosphere, where solar radiation can push the thermometer back up to 4,500 degrees. And finally, there is the exosphere, an endless zone where air molecules slowly thin out into the pure vacuum of space.
Now, the exosphere is really high. They actually detected particles of the Earth's atmosphere on the far side of the Moon during the Apollo program.
As Powell's balloons rise towards space, they leave the world we know far behind. The air thins, and they begin to lose the protective weight of the miles of air above them.
The pressure is dropping. When you finally get to the stratosphere, to the altitude we like to work at, it's only 1/100th that of it is on the ground. It is a whole different world than down here.
The weight of the miles of air above us creates air pressure. We often think of air as weightless, but all those gas molecules add up. Grand Central Station's main concourse contains over 200 tons of air. As gravity pulls the air down, it compresses the layers below, making them denser. This dense air is what we are used to dealing with on the ground. Just a pint of it contains more than 8.5 billion trillion gas molecules. But higher up, around the balloon, there is less atmosphere pressing down from above. The air up here is thinner.
It's like being under 1,000 blankets, and each blanket is a layer of the atmosphere. And we're being pushed under all of these blankets. Now, as you go higher, you're going up through the blankets, so it's pushing on you less, until you're at the top, then above most of the blankets where you don't feel it at all.
That thin air seems alien to us because our bodies and technology are so perfectly adapted to thicker air. We even need it to hear. The gas carries sound through air as pulsing waves of pressure.
Sound is just a wave, like a water wave in a pond. But if you take away the water, there's nothing for the wave to go across. And as the atmosphere gets thinner and thinner, it supports that wave less and less and less.
Finally, in the vacuum of space, there is nothing to carry the wave, and even the largest explosion is silent. School science experiments on board the airship study the dramatic pressure change.
And we call it a PONGSAT, for ping pong ball satellite. And it's real simple. The first thing they do is they have to cut the ping pong ball in half. Then your experiment goes inside. And the simplest and my favorite is where you take like a little mini marshmallow and they just drop it in the ping pong ball. This is satellite construction at its best. And then we take them to the edge of space.
In the thin air of the stratosphere, the marshmallow is no longer held together by high air pressure. Air bubbles inside it expand, causing the spongy candy to bloat outwards and burst open the PONGSAT. Just as the thin air is dangerous for marshmallows, it can also affect flesh and blood. Contrary to popular belief, your blood won't boil. It's held in by your blood vessels. But any exposed flesh will swell out like the marshmallow. And at around 26,000 feet, the air is too thin to breathe. There just aren't enough molecules in every lungful of air. And starved of oxygen, your brain will begin to shut down.
You know, the extreme cold would get you, but the lack of pressure would get you first.
As the balloons rise higher still, they face attack by an invisible bombardment: radiation. Every day the sun radiates a titanic amount of energy, some of it in the form of high-energy ultraviolet rays. These rays pack a powerful punch, and in the high atmosphere, they attack the structure of Powell's balloons.
The UV literally damages the material, and you start getting microscopic cracks in the material, which makes it brittle. Eventually, it just fails, and the balloon pops.
The rays are potential killers, both for balloon and human. They bombard our cells and DNA, triggering cancers. But around 7 miles up, a layer in our atmosphere shields us from 99% of these rays. It is made up of ozone, a rare molecule of 3 bonded oxygen atoms. This can absorb and block high-energy UV rays.
The ozone layer, it's not like this saran-wrapped thick layer or boundary that you pass through. It's actually miles and miles thick, so it's a slow diminishment.
Man-made chemicals used in refrigerators and aerosols have been eating away at this delicate protective layer. Every winter, holes in the shield appear over the poles. The harmful chemicals are now banned, and the layer is beginning to recover. And above it, the fragile air of the mesosphere is shielding us from another deadly barrage from space. In East Texas, Jeff Notkin and Steve Arnold are searching for the remains of cosmic missiles that have been shattered by our atmosphere. Fragments rarer than diamonds and worth their weight in gold. Meteorites. These two professional hunters seek out space rocks buried in the fields and prairies.
This search for meteorites allows me the chance to touch a little bit of what's from out there, bits of the cosmos that have found their way to us.
The hunt has taken Steve and Jeff from Siberia clear down to Chile, and some of their finds have been spectacular.
The largest meteorite I found was 1,430 pounds. It was a large stony iron meteorite from up in Kansas. We didn't realize it was that big of a deal. The media kind of picked it up and ran with it.
He's very modest. It's not only Steve's greatest find, it's one of the greatest finds ever made in meteorites.
The massive space rock has been valued at up to a cool $1 million. But this is a rare find because most meteorites simply don't survive a brush with Earth's atmosphere.
Most of them don't make it to the surface. The atmosphere is our friend in the sense that it protects us from these rocks from space, but for meteorite hunters, it's also not our greatest ally because it burns up a lot of what we're looking for.
Steve and Jeff search for remaining fragments using a custom-built metal detector rig.
Meteorites will have iron in them, and it's ferrous, and so not only will a magnet attract to it, but also a metal detector will be able to pick it up.
Every year, over 18,000 meteorites lock onto a collision course with Earth.
When meteorites encounter our atmosphere, they're traveling at the speed that they acquired while moving through the vacuum of space. And typically, they're traveling at many thousands of miles per hour.
As they head down to Earth, they cut through the outer reaches of our atmosphere. But once the meteorites enter the mesosphere, the air starts pushing back.
We can't see the air around us, and we can only feel it on really windy days like this. But a meteorite encountering our atmosphere definitely feels the air. And that is because it's traveling so quickly. When it encounters our atmosphere, the air in front of the meteorite cannot get out of the way in time. It's almost like the meteorite hitting a solid wall, like a block of concrete.
As the air in front of the meteor compresses, it also heats up to more than 30,000 degrees Fahrenheit. Eventually, it bursts into flame, lighting up the sky. When you see a falling meteorite or shooting star, it's actually the protective shield of air that you see burning, not the meteorite itself. But the friction and heat wears away at the space rock. The hot air actually melts the metal surface. And often the collision with the atmosphere can have a shattering effect, splitting the meteorites along fissures.
This is an actual meteorite, and if this were to encounter the atmosphere at high speed in its current condition, and that's the result.
Only fragments of the original asteroids survived the fall to Earth. Their speed has dropped from 17,000 to 300 miles an hour. Rocks as big as station wagons have shrunk to the size of golf balls. They impact on the surface, forming holes a few inches deep. The chances of finding one are remote.
There we go.
I'll get the shovel.
Right about there, Maestro.
It looks promising, but this time the guys are out of luck.
So yeah, we found a plow, and basically a lot of different types of trash can be in these fields, and so anything that's ferrous, our detector's going to pick up. Meteor wrongs, as we call it, as opposed to a meteorite.
On average, they uncover 75 meteor wrongs for every meteor right.
This is a genuine iron meteorite. This is believed to have once been part of the core of a long dead planet or asteroid. And this was found right here in this strewn field. These remarkable little shapes, indentations on the surface, are called thumbprints, or scientifically regmaglyphs. And that's a feature that's unique to meteorites. And these little markings are caused by the surface actually melting as it flew through the atmosphere. We don't find regmaglyphs on Earth rocks.
The air is constantly at work, making meteorites rare and valuable.
The chances of meteorites surviving their journey through the atmosphere and being found are minuscule. If it wasn't for our atmosphere, we would have little particles raining down on us all the time, and some of them not so little.
The mesosphere's barrier of thin air is the final gift from our atmosphere, adding to the oxygen we breathe, water we drink, and pressure we feel. But as we cross into the layers above, we leave life far behind. John Powell's airships have only reached the upper stratosphere. Kittinger's jump point is below that, in the middle of the stratosphere. The only people who travel through the superheated thermosphere and distant exosphere are astronauts heading for space. One day, these manned space missions may reach out even further, to distant planets with alien atmospheres. Atmospheres that may support their own life forms. Elsewhere in our universe, on distant planets, alien air may support extraterrestrial life. Joel Hagen has spent 20 years imagining how those atmospheres could have affected their inhabitants.
That's where some of the real creative joy comes from, is trying to think about everything that has happened here and then take yourself one notch beyond it and imagine, what haven't I seen yet? And then try to visualize that.
One of the possibilities that intrigues Hagen is life on a gas giant planet.
This is an environment so completely alien to what we're used to. Even a planet like Jupiter, for instance, has no solid surface, just a gradual transition of densities of gases. And I think we might imagine creatures in an atmosphere like that that sort of relied on buoyancy, perhaps being able to generate hydrogen, for example, somehow within their bodies.
These creatures would be like hydrogen-filled blimps, lighter than the air, able to float amongst the gas clouds.
The concept that I have here is to have perhaps colonies of microbes in these sort of tentacle-like structures here. And these microbes generate the hydrogen, which in turn sort of inflates the gas bag here. A creature like this then could sort of float freely at certain levels in the atmosphere.
On other planets, with denser atmospheres, larger, more complex creatures could take to the skies. The thicker air would support them aloft, allowing bulky reptiles to glide and fly.
This creature probably wouldn't be able to fly very well on our planet, but even on a planet like Titan, for instance, it has a surface gravity only about 15% of Earth's, but an atmospheric density at ground level about 1.5 times. Even a person with wings strapped to their arms could fly in an atmosphere like this, so we could have creatures like this.
Hagen bases his ideas on known planets and the evolutionary history of Earth. But it's all pure speculation, until we find life in alien atmospheres.
I would be pretty thrilled just to find microbes under rocks on Mars, for instance. They don't have to walk up and shake hands with me to get my blood up. I would be pretty happy just to know that life has happened twice.
At present, we are alone. Life may have happened just this once. And if it did, then it's only because of our planet's unique atmosphere. As we have soared for miles above the ground, we have journeyed through this ocean of air. The air which shields us, supports us, and sustains us with every breath. Abundant life, it's the hallmark of our planet. But it's water that makes us unique.
Liquid water is the essential environmental requirement for life on Earth. So when we look for life elsewhere, we start first by looking for liquid water.
Our search has taken us to an alien world that seems to defy the laws of physics. A place where water can't exist, but shows us evidence that it might.
We have what we in science call an anomaly.
NASA's Phoenix lander will find out if life is possible on this desert planet. Welcome to Mars, the water world.
Load relief kit crate is in, vehicles responding. Vehicles recovering very nicely from the liftoff transients.
August 4th, 2007 at 5:26 a.m. This Delta II rocket blasts off from Cape Canaveral. In its nose cone is NASA's first robotic Mars scout, the Phoenix lander.
At this point, we have a strong signal from Phoenix via Odyssey.
At NASA's Jet Propulsion Laboratory in Pasadena, California, engineers monitor the progress of the $500 million mission.
All stations, we have confirmed crew stage separation and UHF signal acquisition via Odyssey. Atmospheric entry on my mark. 3, 2, 1, mark.
The new generation lander enters the final phase of its 400 million-mile journey to Mars.
1 minute since LOS, standing by for signal reacquisition.
Phoenix will search the Arctic plains of Mars for the building blocks of life, including carbon, nitrogen, and most importantly, water.
Touchdown detected. Landing sequence initiated.
Phoenix intends to prove that life on Mars is, or was, possible. If it does, then life on Earth is not unique. This is a test simulation, but on May 25th, 2008, the team at JPL attempts this for real.
Primary objective of Phoenix is to explore the Martian Arctic and to determine whether or not conditions for life are there today or existed in the past.
If Phoenix finds what it's looking for, it will change our understanding of the solar system. If there's life on another world, it could mean that the universe is teeming with it, that the aliens of our science fiction could be a reality. Phoenix might even find them. But finding the signs of life on a planet millions of miles from home is an incredibly difficult challenge. The lander hasn't been designed to find life directly. It's been built to find the necessary ingredient for it: water. Chris McKay is a planetary scientist at NASA's Ames Research Center.
When we look at life on Earth, we see an enormous diversity. Organisms that do all sorts of different chemistry, live in all sorts of different environments, but the one thing that all organisms on Earth have in common is a requirement for liquid water. So naturally, when we look for life elsewhere, we start first by looking for environments that have liquid water.
Here on Earth, wherever there's water, there's life. Even in temperatures as extreme as 14 degrees Fahrenheit, organisms can survive. So if we find signs of water on Mars, we might find life too. But why are we looking on Mars? Professor of Geomorphology Vic Baker explains.
30 years ago, a spacecraft called Mariner 9 produced about 9,000 pictures, many of which showed large channels and valleys. And it was very obvious that these channels and valleys are directly analogous to what we see on the Earth, formed by water.
Scientists are stumped by these images. It definitely looks like water erosion. But as far as they know, there is no water on Mars. Its atmosphere is too thin to support it. The air pressure on Mars is less than 1/100th of the Earth's, which means the air on Mars's surface is the same as it is here on Earth at 110,000 feet above sea level. That's 20 miles high, nearly 4 times the height of Mount Everest. Scott Rafkin is a planetary atmosphere specialist at the Southwest Research Institute in Boulder, Colorado.
It's fairly common knowledge that if one goes camping or hiking and you go up to higher altitudes and you go to boil your water, as you go higher up, it boils at lower and lower temperatures. That change in altitude is what you're really doing is changing pressure. As you go up in altitude, the pressure is becoming less and less. And so what happens is that as you go higher up, it becomes easier to boil water. You don't need to raise its temperature as much.
This experiment shows the effects of Mars's atmospheric conditions on water. Gradually removing air from the chamber reduces the pressure. At first, nothing happens. But when the pressure drops to the equivalent of Mars's atmosphere, the water boils. Water normally boils at 212 degrees Fahrenheit, but at this low pressure, it boils at room temperature. On Mars, this happens at just 50 degrees.
The stability of water on any planet is tied to primarily the pressure. And the pressure on Mars is so low that if one could have liquid water sitting out on the surface, it would simply boil.
Mars's ultra-thin atmosphere creates another problem for water to exist here. There's not enough of it surrounding the planet to insulate it. Mars is ice cold. At its warmest, it's just 70 degrees Fahrenheit. At its coldest, the temperature drops to -225.
Now, of course, on Mars we have another problem, which is that it's very, very, very cold. So even if one had the higher pressure so that the water wouldn't boil off, it would just freeze solid, like a rock.
The existence of these channels and valleys that appear water-carved baffles scientists.
The question is, how do you have these two things? How do you have a planet that is cold and dry with a thin atmosphere, and yet clearly, in its past, had flowing water?
Over the years, scientists have offered many theories to explain the features seen on Mars's surface.
People have suggested, well, maybe it's carbon dioxide liquid, or maybe it's lava, or maybe it's wind. Well, wind, lava, carbon dioxide could have formed many of the features we see on Mars, but they can't explain all the features.
And for the past 30 years, this has been the major source of science controversy. And it's the reason that the current NASA program is sort of directed with this euphemism, follow the water.
Using the latest science provided by Phoenix, NASA hopes to prove once and for all that they were made by liquid water, a substance that shouldn't exist on the planet. But the debate is growing more controversial. In June 2000, scientists got very excited about these images taken by the Mars Orbiter camera, a probe that has been circling the red planet since 1997. This one was taken in 1999, and this is of the same location in 2000. The images clearly reveal a changing landscape. To geologists like Vic Baker, these recently formed features look strangely familiar.
On Earth, we would call them gullies. They're sort of on the scale of hundreds of meters, no more than a kilometer. They're patterns like the veins in a leaf or branches in a tree that result from how water falling on the surface organizes itself into larger and larger drainages.
These gullies and alcoves seem to have been recently formed by water. They have appeared in the southern hemisphere of the planet, on slopes that get the least amount of sunlight during each day, one of the coldest parts of Mars. Their similarities to gullies formed by water here on Earth defy logic and the laws of physics. So what created them? Did water flow across Mars in its past? And is it still flowing today? On May 25th, the Phoenix lander, NASA's $420 million mission to Mars, touches down on the red planet to answer two questions that have vexed scientists for decades. Is there water, and could there be life? At the heart of this debate lies this rock that landed on Earth from Mars. Discovered in 1984 in the Antarctic, it's 6 inches long and weighs over 4 pounds. It's called the Allen Hills meteorite, and it's one of just 34 Martian rocks that have been found here on Earth. Johnson Space Center astrobiologist Dr. David McKay has studied this meteorite for more than 10 years.
Allen Hills is unique among the Mars meteorites because it's so old. It is by far the oldest of the known Mars meteorites. And furthermore, with an age of 4.5 billion, it is older than any rock ever found on the Earth.
McKay believes it contains proof life was possible on Mars. Using high-resolution scanning electron microscopes, he examines the meteorite and discovers tiny globules of iron and magnesium carbonate. Elements almost certainly formed and deposited by liquid water.
Carbonates are significant because they show that not only was water there, but it was relatively low temperature.
McKay is convinced that this proves Mars's atmosphere was once very different and could sustain flowing water, so the conditions for life were present. By radioisotope dating the carbonate globules, McKay comes up with a figure. Water flowed on Mars 3.9 billion years ago. NASA's current crop of rovers scouring the planet backs up McKay's findings. This is Meridiani Planum, the landing site of the rover Opportunity in January 2004. It's a dusty area the size of Oklahoma. Photographs relayed back to Earth reveal the soil is littered with countless BB-sized rocks. NASA scientists nicknamed these puzzling objects blueberries. On Earth, similar deposits form, but only in standing water or hot springs. Geologists have uncovered blueberry-like clusters dating back millions of years in Lake Superior and near the hot springs of Yellowstone National Park. Their discovery on the vast plain of Meridiani Planum suggests this area was once saturated with water, or was even an ancient lake. In fact, closer examination of the surface of the planet reveals that much of it was once a water world. These images, taken by a high-resolution stereo camera aboard the Mars Express spacecraft, reveal Mars's watery, almost Earth-like past. This is a large depression called Ionic Chaos, and next to it an outflow channel called Eris Vallis. They're the remains of Martian river systems, and to planetary geologists like Jim Rice, clear evidence of ancient catastrophic floods.
We took every river on Earth and put it in one spot, had them flowing at the same time. Some of these flood channels on Mars, when they were in full force, were 20 or 30 times bigger than those.
What was it that happened in the Martian past? Why do we have a planet today that is very cold and dry and gives every indication that we don't have liquid operating on its surface? Why in the past did we form these channels?
If Phoenix can figure out if water flowed across the surface of Mars in the past, it will explain the valleys and canyons we see today, and take us one step closer to discovering if water still exists, and even life. Now the Phoenix mission can confirm what the experts suspect.
It must have been warmer, at least for some period of time, so that we could have liquid water on the surface. And the pressure must have been higher than it is now, or the water would have boiled away.
Early in its evolution, Mars was much warmer. In fact, it was boiling. $4.6 billion years ago, our sun bursts into life, and our solar system forms around it. Both Earth and Mars are huge balls of lava, boiling at over 12,000 degrees. Slowly, they begin to cool. Dr. Peter Smith heads up the Phoenix mission from its base at the University of Arizona.
Earth and Mars formed at about the same time, but Mars is only half the diameter of the Earth, and therefore it would cool more rapidly.
Mars's size proves to be the crucial factor in its transition from a fiery molten ball into a warm and wet planet. In this demonstration, two globes are used to represent Mars and our own planet, Earth. These scale models exactly replicate the difference in size of the two planets. Mars, shown here on the left, has half the diameter of Earth. Both spheres have been heated to the same temperature. Now they are cooling naturally. Infrared time-lapse clearly shows how quickly the smaller sphere representing Mars cools. Mars was cool enough for water at a time when Earth was still a red-hot ball. This water comes from comets. The early solar system is littered with large asteroids and comets made up of ice. As they crash into the planets, the ice melts. On super-hot Earth, the water boils away instantly. But Mars is cool enough to hold on to the huge quantities of water released by impacts.
And in that cooling, liquid water would be stable on the surface long before it would be stable on the Earth. And so during that period, it may be that you had rains and valley systems and lakes and all kinds of Earth-like situations.
Scientists believe that 3.9 billion years ago, Mars had the climate and atmospheric conditions to support liquid water, an essential ingredient for life.
Now, in the early days of the history of our solar system, this planet, the Earth, was not a good place for life to develop. We had noxious gases all over the places, volcanoes belching out all sorts of stuff. Mars was warm and wet and wonderful. It was the most likely place for life to develop.
Today, Mars is no longer warm, but is it wet? Understanding what happened to Mars's water is the primary goal of the Phoenix mission. Its success might hold the key to answering a 30-year-old question. Does water still exist on Mars? Scientists are now certain that Mars was once warm and wet. Pictures of ancient riverbeds, blueberries on the surface, and carbonate globules inside the Allen Hills meteorite confirm this view. But if there was water billions of years ago, where is it today? The question of whether water still exists on Mars will only be settled when NASA physically finds it. And that's the job of the Phoenix lander. It's being sent further north than any previous mission, to a site chosen because frozen water might sit below the surface. In 2003, NASA's Odyssey orbiter produces this image. Using its gamma-ray spectrometer, the spacecraft maps levels of hydrogen in the upper 3 feet of Mars's surface. Since high levels of hydrogen indicate the presence of frozen water, scientists think that these blue and violet areas, the densest concentration of the element, reveal an enormous frozen reservoir.
In fact, there's so much water in the polar areas and the nearby ice terrains that if you spread that water around the surface of Mars, that alone would inundate the surface of Mars on the order of 6, maybe 10 meters deep.
Phoenix's first job is to confirm that the hydrogen-rich area is in fact made up of water. Then scientists can begin to piece together the chain of events that lock the water under the planet's surface. Maybe then they'll begin to understand how the recent wet spots appeared. Some scientists believe they are a remnant of ancient climate change. Mars cools much more quickly than Earth, allowing water to exist on its surface. But a drastic shift in atmospheric conditions means it can't hold on to it. Earth's large molten core generates a magnetic field which protects our atmosphere from solar radiation. But Mars's small core cools so much that it no longer produces an effective shield. Solar wind blasts away its atmosphere and most of its water. Pressure falls and the temperature plummets. Whatever water it has boils away or freezes solid, leaving the Mars we see today, a frozen world. Up until recently, scientists believed that Mars's core is so cold that it is no longer able to crack and move the planet's surface.
The Earth releases a lot of its heat continuously by a process that's known as plate tectonics, where the continental masses of the planet are actually shifted by the formation of new crust in the ocean basins. Mars doesn't have that.
But the discovery of the gully features, the wet spots, suggests that Mars's core hasn't cooled as much as they thought.
Because it can't release its heat as efficiently as Earth, one idea is that this heat builds up with time, and episodically there's kind of a burst of heat release that will melt the ice in the Martian permafrost. And that water comes onto the surface, perhaps associated with gases that change the composition of the Martian atmosphere to a greenhouse kind of condition. So you have a temporary, unstable state where Mars is warmer and has water on the surface.
These small flash floods could be the wet spots that dot the surface of the planet.
It's natural to suspect that maybe this volcanism that has happened in recent history and the water activity are somehow related. But this is one of the mysteries we're trying to investigate, and I think it's one of those that the Phoenix lander may be able to shed some light on.
By finding ice and analyzing its composition, the Phoenix lander is designed to map the planet's ice history. It will tell us how geothermal activity and atmospheric change have affected Mars's ancient water.
Load relief kick crate is in. Vehicles responding. Vehicles recovering very nicely from the liftoff transient.
Phoenix's quest represents a journey into the unknown.
Up to now, all of our exploration of Mars has been superficial. We take pictures from orbit, we drive around on the surface, and maybe we dig down this deep, either by dragging it with the wheels or with a little arm or something. We maybe get down this far, and that's it.
But Phoenix is set to change this. It's designed to endure Mars's northern latitudes and to analyze subsurface ice. NASA hopes its findings will throw light on how water interacts with the geology of Mars, the key to unlocking the story of past atmospheric change. In order to achieve this goal, it's been built to do something no other Mars lander has done before.
Phoenix is going to arrive on Mars and land and dig.
A sophisticated robotic arm will dig down 3 feet into the frozen subsurface to where the layer of water is believed to be. At nearly 8 feet, the arm is the most important tool on the lander. It's designed to dig trenches, scrape ice, and deliver samples to other instruments on the lander's deck. No one knows the capability of this arm better than Phoenix's lead scientific investigator, Dr. Peter Smith.
The robotic arm in digging on the surface is doing something very difficult because it's being controlled from 100 million miles away. And so the interaction of using the arm and seeing through the eyes of a camera is not simple. It's like going out to drive a semi-truck with never having driven one before. The truck works, but learning how to shift 18 gears is not so easy.
If working properly, Phoenix's robotic arm will drop ice samples into a device called a Thermal and Evolved Gas Analyzer, or TIGA for short. TIGA has 8 tiny ovens, about the size of an ink cartridge in a ballpoint pen. Not unlike this one. Once a sample is successfully sealed in an oven, the temperature is slowly raised at a constant rate. As the temperature edges up to 1800 degrees Fahrenheit, the ice and other volatile materials in the sample vaporize into a stream of gases.
So if you think about what happens in your kitchen when you put, say, some sort of food in the oven and you start to heat it up, it's cooking nicely at 200, 300, 400 degrees. But if you start to crank that oven up 800, 900 degrees, 1,000 degrees, what's going to happen to the organic materials in there? Well, they're going to turn to smoke. They're going to come out, and like in my kitchen, they're going to set off the smoke alarm. And you're going to be doing an experiment just like Tiga.
Roasting the samples of soil and ice at 1800 degrees releases what are called evolved gases. A mass spectrometer will then scan these gases for minute quantities of hydrogen, oxygen, carbon, and nitrogen, the elements of life. But Phoenix's sophisticated instruments do have a limit. Each of its 8 ovens can be used only once. So as it digs down, it will take samples at 8 different depths. NASA hopes to then map the changing character of the ice. Scientists hope these precise measurements will reveal the evolution of water on the planet and possibly uncover the existence of life. To get a head start on the kind of data the lander might send back, the Phoenix scientists set out to replicate their experiments here on Earth. The geology of Mars and Earth is surprisingly similar. Mars is a cold, dry desert landscape of sand and rocks. But both planets share land features like volcanoes, canyons, and valleys. This is the most Mars-like place on Earth, the Antarctic.
Mars, when it was at its warmest and wettest, would have been like Earth at its coldest and driest. That's why, to me, going to the dry valleys of Antarctica is the next best thing to going to Mars.
Here, Chris McKay and Peter Smith are going to do on Earth what Phoenix will be doing on Mars.
The idea is to make the connection between what Phoenix will measure on Mars with what Phoenix would measure in the dry valleys of Antarctica.
They're digging down to ice to see if life, or the conditions for life, exists in this inhospitable terrain.
We go from a surface soil, which is kind of reddish and definitely of a different character than the lower soils, and we're going to measure layer by layer down to ice. We're using instruments on the deck of the spacecraft, and our robotic arm scoops up samples as it digs down and presents them to the science instruments, which analyze them right there on Mars. I think just by looking at these soils here, you can tell that liquid water's been at work. If we could see that on Mars, we have a place where we have a habitable zone and perhaps a place where life could live.
McKay and Smith's analysis of Antarctic ice reveals that life can exist in the sub-zero temperatures found on Mars.
It's really quite phenomenal what we can find in the dry valleys and in the high Arctic, how life can make do with small, transient amounts of liquid water.
These life forms are called extremophiles. They're microscopic bacteria that thrive in extreme environments. They were first discovered 40 years ago in the 160-degree hot springs of Yellowstone National Park. Since then, others have been found living deep under the ocean, in supersaline environments, even in the uranium-rich pools of water in nuclear power stations. But it's the ones that live in the sub-zero temperatures of Antarctic ice that interest the Phoenix team. They reason that if microbes can be found here, then why not on Mars? So if Phoenix finds ice, it might just find evidence of life locked inside it.
The other remarkable thing about polar deserts is how well ice and cold in general preserves evidence of life. We know that you can go up into permafrost in Siberia and dig out mammoths that have been frozen for 10,000 years or more. On Mars, we're hoping for the same effect. We're hoping to find, frozen in the ice on Mars, evidence of life that may have been preserved maybe for millions, but maybe even also for billions of years. Frozen micro-Martian mammoths, if you will.
Not only will Phoenix detect changes in atmosphere and temperature, it has the ability to identify organics, crucial to the search for life.
Our mission was designed specifically to touch water in the form of ice and to try and understand the properties of that ice, its history, its interaction with the soil, its interaction with the atmosphere, and really explore the question of is there or was there ever life on Mars?
By analyzing the soil samples, Phoenix might finally identify the building blocks of life: carbon, hydrogen, oxygen, and nitrogen on Mars.
And if we saw the organic materials, energy sources, and liquid water present in the past, we would say this is a habitable zone, and perhaps some sort of Martian life could live there.
With the Phoenix mission, NASA's 30-year search for water on Mars could finally come to an end. And by following the water, it might just find life. May 25th, 2008, NASA's Phoenix lander reaches the end of its 9-month-long journey to Mars. It now begins the hunt for life, or at least an environment that could have once supported life. But does NASA really think it can find this on the frozen wastelands of Mars? The answer is yes. This is because of an accidental discovery made by the rover Spirit.
Spirit's most significant scientific discovery came 1,200 days into its 90-day mission.
In 2007, a moving part on Spirit malfunctions. The failure leads to the best evidence yet that Mars was once capable of supporting life.
The right front wheel on Spirit doesn't turn anymore. It's failed. But the one good thing, the silver lining here, is that as we drive and we drag that wheel through the soil, we dig a trench. And every now and then, something interesting will pop up in the bottom of that trench.
X-ray analysis of a patch of soil churned up by the stuck wheel yields unexpected results. It is composed of about 90% pure silica.
That was just a complete unexpected discovery, pure serendipity, and frankly, if the right front wheel had been working properly, we might not have found it.
This $320 million breakdown reveals more evidence of water. On Earth, high levels of silica occur in only 2 places: hot springs or fumaroles. Both environments bubble with water and life.
The thing that's important about the silica discovery is that you can go to hot springs and you can go to fumaroles on Earth, and in both instances they're teeming with microbial life.
Spirit has discovered evidence of a habitable zone on Mars, a place where extremophiles like those on Earth could have thrived, and may even exist today. What's more, the idea of Martian life is backed up by the 4-billion-year-old Allen Hills meteorite. Structures inside it reveal what some believe is the first real evidence of Martian life forms. David McKay heads the team that made the discovery.
We discovered in Allen Hills what we concluded was strong evidence for past life. That evidence consisted of, number one, some little tiny fossil-like features that are similar to fossils known to occur on Earth. Number two, we found that there were crystals made of an iron oxide, which are also always associated with bacteria on Earth.
McKay and his team believe that the Allen Hills meteorite is proof that life existed on Mars. When they announced their discovery in 1997, most scientists were skeptical.
The discovery of fossils in the Martian meteorite was always problematical. They weren't really biological structures, they were just little round and little oval-shaped things. And people quickly realized that if you pick up any piece of rock or dirt and examine it at that scale, you often see little round and little oval-like structures that have nothing to do with biology.
But Spirit's discovery of silica on Mars has reopened the debate about Martian microbes. If extremophiles can be found in similar environments on Earth, then why not on Mars? Will Phoenix find the evidence that backs up McKay's belief that life existed on Mars? If it does, the implications will be profound.
You may think that if we find life on Mars and it's just microbes, who cares? Why is that important? But within those microbes could be the potential for all of the richness and complexity of life like we see on Earth. In the same sense that an acorn is an oak tree, a single organism on Mars could represent the potential for complex ecosystems for animals and plants and even human-like intelligence. Even if on Mars that seed didn't grow to its full potential, if the acorn didn't become an oak tree, it's still interesting because it tells us that on other worlds, on other stars, it would have fully developed. We're not alone.
It's an astonishing prospect, one that the Phoenix mission is poised to solve.
Well, when Phoenix lands down on Mars and sends back its first signal that it lands successfully, I will breathe a 5-year-long sigh of relief.
But before NASA's latest probe can answer tough questions about life and our place in the universe, it first faces its biggest challenge: descent and landing. NASA's latest mission to Mars will try to answer some fundamental questions about the red planet and the nature of life in the universe. When Phoenix begins searching ice for traces of life, it takes us closer to understanding our place in the solar system. Is life on Earth a quadrillion-to-1 miracle? Or does it appear wherever and whenever the circumstances are right? Before it can answer these questions, Phoenix has to safely get to Mars. NASA's probe approaches the planet at 74,000 miles per hour.
All stations, Heliocom. At this point, we have a strong signal from Phoenix via Odyssey.
On May 25, 2008, at 7:46 p.m. Eastern Standard Time, the team at JPL begins slowing the spacecraft down for a soft landing on the planet's surface.
It lost the X-band signal from the DSN does indicate an expected cruise state separation.
This man is responsible for bringing its speed down from 74,000 to 5.5 miles an hour. He's Gentry Lee.
The risky part of the mission begins as we near Mars. When we hit the top of the atmosphere, the process of slowing down begins. And in that 6 to 7 minutes, we slow down from tens of thousands of miles an hour to single digits miles per hour so that we can land softly.
It's a process that involves 3 distinct phases. They're called EDL: entry, descent, and landing. Each is potentially deadly. Friction from the atmosphere slows the craft to about 750 miles per hour.
First, you have a heat shield, which takes this enormous potential energy and converts it into heat. That's 99% of the deceleration. Then when it's done, out pops a parachute, and it takes another 99% of the speed out.
The parachute's performance is crucial to the success of the mission. Up to this point, Phoenix's EDL is identical to any other Mars mission. But unlike the rovers before it, Phoenix has no airbags to cushion its landing. Instead, it uses 12 descent rockets clustered around the hull to slow down. In the final 34 seconds of descent, they fire rapid pulses, carefully timed to bring the lander down at 5.5 miles an hour. If Phoenix's engines fail, its terminal descent will have been just that. For controllers, this is one of many things that could have gone wrong.
And then, of course, will come the moment when it's too late to even ask any questions.
Standing by for possible flashing blackout.
Did the radar see the ground properly? Did the computer interpret the information properly? Did the pulsing engines do what they were supposed to do? I can't wait. Will somebody please tell me now?
On May 25th, 2008, at 7:53 p.m., Phoenix starts its descent.
Ground relative velocity 90 meters per second. Touchdown signal detected. Landing sequence initiated.
The landing is a success. For the team, this is the culmination of 5 years' hard work, and yet the mission is just beginning. These are the first images Phoenix sends back to Earth. The search for life on the red planet begins. Saturn, one of the most mysterious planets in our solar system. Now the Cassini-Huygens mission is exploring this enigmatic world and its moons. For the first time, it allows scientists to see what lies below Saturn's upper atmosphere and investigate the origin of its incredible rings. A probe touches down on the largest moon, Triton, to search for a world like our own and the possibility of life.
Five, 4, 3, 2, 1, and liftoff of the Cassini spacecraft.
4:43 a.m. October 15th, 1997. An 1,100-ton Titan 4B rocket launches from Cape Canaveral. It carries with it Cassini-Huygens. Its destination lies almost 900 million miles away, at the awe-inspiring planet Saturn. A huge gas giant, orbited by at least 60 moons. Saturn is the second largest planet in the solar system, over 750 times more massive than Earth. It's a gassy world without solid surface. The last mission to this mysterious planet launched over a quarter of a century ago. The Voyager spacecraft sent back these images, showing a planet shrouded in thick banded cloud. Onboard infrared cameras spot what looks like storm activity beneath the haze. Something big is brewing on Saturn.
The problem with Voyager missions is that they were flyby missions. They were one-time snapshots.
Voyager can't stop to investigate. Its flight plan is fixed. Scientists can only gather limited data. Voyager 1 also skims the atmosphere of Saturn's largest moon, Titan. Scientists are shocked at what it finds. Its instruments detect organic compounds in the atmosphere. These are similar to the compounds that provided the raw material for life on Earth 4 billion years ago.
In a way, Titan is a glimpse back in time to processes that may have been occurring on the early Earth that may have led to life.
But once again, Voyager 1 can't stop to investigate. It hurtles off at 39,000 miles per hour into the cold outer reaches of the solar system. The Voyager mission makes tantalizing discoveries, leaving scientists with more questions than answers. They are determined to return to the mysterious moon and take a closer look.
We want to understand our own origins. We want to understand why the Earth came to be the way it is and how life came to develop here.
Scientists believe by unlocking some of the secrets within Saturn and its moons, we could learn how our own world developed and how life began. Cassini is one of the most scientifically advanced spacecraft ever launched. It will explore Saturn's atmosphere using an array of high-tech cameras and sensors. Cassini carries with it a probe called Huygens. This will deploy to Titan, Saturn's largest moon. It will plunge through the thick atmosphere and land on its surface. But first, Cassini must make the long haul through 2 billion miles of space. The mission control team used the gravitational pull of our neighboring planets to slingshot the spacecraft around Venus, Earth, and Jupiter, giving it enough momentum to reach Saturn. After 7 years of flight, Saturn looms into view. Cassini captures this stunning image of the gas giant. But before it can get close enough to begin its detailed exploration, Cassini must pass through the rings. The rings are chaotic and dangerous. Made up of billions of particles of ice and rock, circling around the planet at high speed. Some chunks are as big as houses. The only way through is to navigate a gap between the rings. Dr. Jeff Kuzi is in mission control as Cassini approaches the gap.
The gap isn't something you would see with your eye. So it wasn't exactly like there was a huge, tight tolerance, a narrow, threading the needle kind of a thing.
Tension builds as the high-risk maneuver begins. Cassini fires its rocket engines to position itself and heads for the gap. Its antenna points away from Earth. Communication is temporarily lost. Dr. Larry Esposito waits for the signal to return. The sign that Cassini has made it through in one piece.
Everyone was holding their breath, waiting for the signal to come from the spacecraft to show that it had successfully passed through the ring plane.
Several hours later, they get the signal.
The Doppler has flattened out.
Cassini has made it through.
Once that happened, the silence ended, broke into cheers, applause. People hopped up, shook each other's hands. Some people hugged each other. It was a great moment of success after decades of planning.
For the first time, a spacecraft has entered orbit around a planet in the outer solar system. And for Dr. Tony Del Genio, it's in the perfect position to start exploring this gas giant.
The beauty of the Cassini mission is that for the first time, we get to go into orbit around a planet like Saturn, and for years observe it over and over again from different angles. And by putting that together over this long period of time, finally some of the secrets start to be revealed to us.
The first task is to explore what lies beneath Saturn's thick upper atmosphere. Cassini maneuvers towards the South Pole. There, its instruments reveal an unexpectedly familiar phenomenon. A monster hurricane-like vortex. This actual image clearly shows the storm and its scale.
This feature is more than 1,000 miles across, so many times the size of a real hurricane on Earth. And what you're seeing is a sequence of images showing the clouds rotating around the South Pole.
This is the first hurricane-like storm ever detected on any planet other than Earth. Like hurricanes on Earth, it has an eye circled by a gigantic column of cloud. But this one towers 45 miles high. Around it, winds rage at 350 miles an hour. Cassini's cameras zero in on the high-altitude clouds in the upper reaches of the eye wall. Temperatures here are minus 167 degrees Fahrenheit. The pictures capture what must be a flurry of ice crystals. Scientists are enthralled. Like Earth, Saturn has storms with swirling clouds, strong winds, and even snow.
It definitely snows on Saturn in the upper reaches of the storm systems that we see. I think we're pretty confident that there would be large ice crystals. When you got down much deeper than we can see to in the images, then we would expect actual liquid water rain to be falling out of the bases of those clouds.
On our planet, hurricanes are fueled by the ocean and ultimately the sun. Saturn is far too distant to draw the kind of solar power its monster storms need. So what drives them?
When you get into a gas giant atmosphere like Saturn, once you get a wind going, you can maintain it for a long period of time without a solid surface underneath it to dissipate it very quickly. But still, slowly over time, if you didn't somehow put energy into the system, the winds would still dissipate.
Now scientists investigate the theory that the energy for the storms comes from deep inside the planet. It's a theory they've never been able to prove. But at a laboratory in France, an extraordinary experiment is trying to verify its basic principles. Cassini captures these images showing a monster storm on Saturn. A gigantic hurricane 2/3 the diameter of Earth rages at the planet's south pole. Winds encircle the central eye at over 350 miles an hour. Scientists want to know what fuels these storms. Saturn is too far from the Sun for them to be driven by solar energy. The power source must lie elsewhere. Many scientists believe it comes from deep within the planet. At the Coriolis Laboratory in France, astrophysicist Peter Reed searches for evidence to support the theory. He is using an internal heat source to recreate Saturn's turbulent atmosphere.
The overall objective is to try to come up with an understanding of what processes actually drive the winds and organize them into banded structures, and into these sets of alternating eastward and westward jet streams on Saturn and the other gas giants.
Inside this huge rotating tank is almost 40,000 gallons of fluid. This acts like Saturn's gases. A heater sits in the base of the tank to simulate a heat source deep inside Saturn. Suspended in the fluid are tiny light-sensitive particles.
So these particles act basically like clouds in Saturn's atmosphere, so they'll be carried around by the winds, and this will help us to actually trace out where the vortices and the jets are actually occurring.
Reed wants to see if currents and vortices develop in the same way they do on Saturn's surface. The tank spins to mimic the rotation of the planet. The tiny particles start to spread out and interact. Slowly, the particles begin to swirl and create vortices.
Okay, so we can see evidence of a jet structure, and then here we can see a very nice rotating structure, which is basically an anticyclonic vortex.
Compare these to Saturn's twisting patterns of clouds. The similarities are striking. Reed's experiment suggests that a heat source within Saturn could fuel the raging storms. But what lies in its center that could generate that much heat? The gas giant is approximately 75% hydrogen and 25% helium, with traces of water, methane, and ammonia. Scientists believe that, like Earth, Saturn has a hot core. Earth's internal energy comes from radioactive materials in the core and residual heat from its formation. But here on Saturn, scientists think heat is generated by highly pressurized gases. Deep down in Saturn's atmosphere, the pressure of the gas builds. Near the core, the pressure is several million times higher than on Earth's surface. It's so powerful that the hydrogen and helium gradually turn from gases into strange metallic liquids.
If you get deep enough, then the hydrogen and helium become so dense that they don't behave like a gas anymore. They behave more like an electrically conducting metal.
This liquid swirls around a rocky core that is roughly the size of Earth. But just as oil and water can't mix, the liquefied metallic elements can't hold together. The heavier helium separates and sinks through the hydrogen. Scientists believe this movement creates friction that generates heat. Cassini is looking for evidence supporting this theory by measuring the precise abundance of helium in the atmosphere. It's already amassed a vast amount of data. There's so much that it will take years to analyze. Scientists hope to find out for certain how Saturn can give out 3 times more heat into space than it receives from the Sun. Cassini is unveiling Saturn's turbulent activity in unprecedented detail. Now its main engines fire, and mission control steer the spacecraft outward to explore one of the greatest mysteries in the solar system: Saturn's chaotic rings. Saturn has the largest and most spectacular rings in the solar system. The Voyager missions first revealed their awesome scale more than 25 years ago. The Voyager spacecraft show that the rings are chaotic. They're made up of billions of chunks of ice and rock colliding into each other.
If you were to fly over the top of the rings very close so you could actually see them, you'd see something that would look a little bit like a flying boulder field. Small particles ranging between a fraction of an inch in size and maybe a couple of yards across.
The turbulent rings got scientists thinking. The particles orbiting Saturn resemble the disk of gas and dust that encircled our young sun 4.5 billion years ago. The particles started clumping together, growing larger and larger, until after millions of years, they eventually formed the planets in our solar system. Could the same process be occurring inside Saturn's rings? Is this a good analogy for how planets may grow? Cassini sends back these stunning, highly detailed images.
I was very excited to see these beautiful, beautiful images. We're going to learn a huge amount just from the first couple of images.
Cassini uses an ultraviolet imaging spectrograph to map out the ring's structure with remarkable clarity.
The spectacular detail that we saw was just an eye-opener, and we stood amazed to see the structure that was in the rings, much more than I had personally expected.
As the particles pass in front of distant stars, the UV spectrograph measures the amount of starlight shining through. Areas that contain a lot of particles block starlight and appear darker. Where there are fewer particles, more light passes through. Scientists interpret the darker regions as temporary clumps of ring particles. They are known as moonlets. Cassini captures them on film for the first time. They appear as bright lumps within the rings.
These big boulders may very well be nothing but an agglomeration of the smaller ones. And these agglomerations may come and go with time as they bump into each other. They may just fall apart and collapse, and then they may reform by their own gravity and stickiness on the surfaces.
Scientists are fascinated by the images. They think this process happened in the early solar system. 4.5 billion years ago, the planets grew from microscopic specks to the size they are today.
The interaction between the moonlets and the ring particles is exactly like the interactions between a planet and the dust that's collecting to make that planet grow.
Cassini's spectacular images offer new insight into the processes behind the formation of our own world and the entire solar system. But where did all the material that makes up the rings come from? In its infancy, the solar system was a violent place. Comets and asteroids regularly collided with young planets, creating massive explosions and leaving behind scars that we can still see today. This image, modeled from real data, shows Saturn's tiny moon, Mimas. This giant crater dents its surface, a scar from a gigantic impact. Mimas was lucky. It survived the impact. But scientists think that Saturn could have lost one of its other moons completely, shattered into billions of fragments.
Imagine an object coming in that's the mass of a small planet or a big comet coming in. There's a huge amount of energy there. It could actually rubbleize it pretty well.
Saturn's powerful gravity could have captured the fragments and over time compressed them into a flat plane around its equator. These strange rings may be the result of the solar system's most intense period of planetary bombardment. They may also unlock the secrets of the solar system's birth 4.5 billion years ago. Cassini's next stop provides scientists with another opportunity to step back in time, to a world like Earth before life evolved. This is the mysterious moon, Titan. Cassini has crossed over 2 billion miles of space to reach Saturn and its moons. It carries with it a secondary space probe called Huygens, designed to land on Titan, one of Saturn's 60 moons. Titan is massive. It weighs almost twice as much as Earth's moon. It's an object that's perplexed scientists for decades. In 1980, Voyager 1 sends back these intriguing images of a world shrouded in a thick orange atmosphere. Analysis reveals that this is mostly made up of nitrogen, just like Earth's. The spacecraft also detects water and traces of organic compounds like ethane and carbon dioxide. Compounds that could provide the raw materials for life. Titan's atmosphere appears to be remarkably similar to that of early Earth. Now Huygens returns to pick up where Voyager left off, to search for signs of life. Dr. Carolyn Porco was a young PhD student on the Voyager missions.
You can imagine that for those of us who had been involved with the Voyager mission 24 years earlier, that there was a tremendous amount of anticipation in returning to the Saturn system.
Cassini's sophisticated cameras alone can't fully penetrate Titan's thick atmosphere. What's on the surface beneath the thick haze?
Our first pictures of Titan were very mystifying. In fact, our images are painted on this globe, and it's very difficult if you look in details to see exactly what you're looking at.
Cassini's probe, Huygens, is designed to solve this mystery. The probe hits Titan's dense atmosphere at over 13,000 miles per hour. At first, its cameras only transmit these images of a thick yellow haze. But at around 30 miles up, Titan's surface comes into focus.
It's just very difficult to describe accurately what it was like to see the first images that they showed of the surface of Titan, because they were mind-blowers.
These images show an extraordinary desert-like landscape with low hills and rolling plains. But mission engineer Dr. Ralph Lorenz worries where Huygens will touch down.
We had no idea what it was going to land on. We didn't even know if it would survive landing. It could have landed in a lake of liquid hydrocarbons. It could have landed on a solid sheet of ice or a sand dune.
To the relief of all, Huygens lands on level ground and survives. It's the first probe to touch down on another world in the outer solar system. Onboard cameras reveal an eerie alien landscape. Lorenz rigged the probe with an instrument to analyze the composition of Titan's surface.
One thing it did is it had an instrument called a penetrometer, which was rammed into the ground and told us how hard the surface was. The texture was like damp sand or even a soft clay, and there were indications that there might have been a pebble or a crust on top, and there was even the joke that the surface was made of creme brulee.
The penetrometer reveals Huygens has touched down on soft ground, but not just any ground. Its camera shows smooth, round rocks, similar to those found in a riverbed.
There were a lot of rounded pebbles around, and the way you get rounded pebbles is that they're tumbled in a stream. And so this area, which had river gullies, must have been rained on sometime in the past, and the rain washed down, tumbling these pebbles.
Huygens discovers signs of liquid on the moon's surface.
So right away, there was this unambiguous sign of a process that we knew how to interpret. So this was tremendously exciting. It said there had to be liquid something flowing on the surface of Titan.
But is the liquid water? Huygens' thermometer registers the surface temperature as 290 below zero. In this bitter climate, water would freeze as solid as rock. But if water didn't carve this riverbed, what did? As Huygens continues to probe from the ground, Cassini moves to the moon's uncharted North Pole. Its radar penetrates the smoggy atmosphere to reveal dark patches. These indicate something astounding: lakes. Liquid may still flow on Titan's surface. But what liquid can withstand freezing temperatures? Cassini's visual and infrared mapping spectrometer picks up a dramatic cloud system. It's enormous, engulfing almost the entire North Pole. Scientists suspect these clouds could supply the liquid that appears to fill Titan's lakes. Cassini homes in on the clouds and finds they are made of methane. It seems that Titan's surface has been carved not by water, but by liquid methane.
We've counted up the volume of liquid in some of these lakes, and it's hundreds of times the amount of all the liquefied natural gas, all the oil on Earth.
The super cold temperatures on Titan allow methane to exist as a liquid. Any water on this moon is frozen solid. Surface conditions are not conducive to life. But Titan's atmosphere is another story. Scientists focus in on the tiny particles suspended in Titan's atmosphere, first discovered 25 years ago. They are a cocktail of organic molecules, the stuff of life. Molecules like these existed on Earth 4 billion years ago. If scientists can understand how they form on Titan, they can figure out how they developed into life on Earth. Cassini isolates the exact mix of molecules and transmits its findings back to mission control. Astrobiologist Dr. Chris McKay has been trying to recreate Titan's atmosphere in the lab, using the data from Voyager.
As soon as the Cassini results came in, we scrambled to change our experiments, to line them up with the new information. It was like working on a problem for a decade and then finally seeing a glimpse of the answer in the back of the book and realizing, aha, this is the way to go.
McKay now tries to use this formula to turn simple organic molecules like methane and nitrogen into the building blocks of life. In his lab, he simulates Titan's pressure, temperature, and nitrogen-rich environment.
Here is a tank of methane and nitrogen. This is the starting mixture for Titan's atmosphere. It flows through the apparatus into our reaction chamber. So now I'm going to turn on the energy source, and this flow of methane and nitrogen will experience the same kind of energy processes that are going on in Titan's upper atmosphere.
Then McKay uses electricity to simulate the sun's ultraviolet radiation.
We have Titan in a jar.
After a few hours, the simpler molecules turn into complex nitrogen-rich substances called tholins. These lab-made tholins are almost exact copies of those found on Titan. Understanding how they form gives us valuable insight into the origin of life on Earth.
One overall question in studying Titan and comparing it to the early Earth is the question of how unusual is the sort of chemistry that led to life on Earth? Is it very rare and it happened on Earth because of very unusual circumstances? Or is it commonplace organic chemistry that we can expect on any world that's like Earth or even like Titan? And if we find that there's a common theme, a common way in which this kind of process goes, maybe the steps that lead to life are commonplace, and therefore life is commonplace.
The Cassini mission to Titan reveals how life could emerge on other worlds. On the surface, Huygens' batteries die out. Its landing represents one of the great achievements in the history of space exploration. Huygens provided a spectacular view of Titan and returned over 750 images and over 3 hours of data. Cassini abandons Huygens on Titan and heads for another moon, which scientists believe could be its greatest conquest, Enceladus. Cassini continues exploring the Saturnian system. In its sights, the moon Enceladus. Covered in ice, Enceladus is one of the brightest objects in the solar system. Cassini's cameras capture these detailed images of this dazzling, frozen world. Its ancient wrinkled surface is made up of fractured plains, craters, and folded mountains. But as it skims past, Cassini's magnetometer registers some kind of disturbance. This is the actual recording. The moon creates fluctuations in Saturn's immense magnetic field. But how? The magnetometer detects gas coming from the moon's surface. Experts suggest it must have some kind of partial atmosphere. Planetary scientist Professor Bob Brown thinks this is impossible.
They said, hey, you know, we're seeing evidence of a tenuous atmosphere around Enceladus. And many of us responded with skepticism because an object like this can't have an atmosphere.
Enceladus is just 300 miles across. It has too little gravity to hold on to an atmosphere for very long. But things are about to get stranger.
The magnetometer group told us the atmosphere around Enceladus seemed to be concentrated around the South Pole, which is even weirder. Atmospheres don't do that. They distribute themselves uniformly around an object.
The team is mystified. What could create a strange, localized atmosphere? Cassini moves closer. The spacecraft captures this stunning image. Giant geysers on the surface of the moon appear to throw out huge plumes of vapor. The unidentified gas blasts over 400 miles into space.
To see this image, okay, where we have a dozen to 24 jets, narrow jets, just emerging from the South Pole, was, you know, it's one of those things that a person who lives the kind of life I lead lives for. Okay, it was just one of those discoveries that, you know, you're not going to make often in your lifetime.
Cassini's spectrograph analyzes the vapor of the jets. It contains water. This discovery is completely unexpected. Could liquid water exist on this frozen moon? Cassini is looking for liquid water on Enceladus. It zeroes in on an area of the moon covered with cracks.
But one of the things that was absolutely stunning about this is that when we got into these areas where these cracks are, they're clearly a lot warmer. It may very well be that the temperatures there are as high as 0 degrees C. It may very well be that they're high enough that liquid water is literally very, very close to the surface.
Cassini has found a hot spot, an area warm enough to support water in its liquid form.
That was just, you know, mind-blowing. Like, what could be possibly producing this? It's one thing to find a body to be warm. It's another thing to find that it's only warm in one location.
Scientists are baffled. What generates these pockets of heat? Enceladus's orbit is elliptical. Its distance from Saturn varies over time. One theory is, as it passes close to Saturn, its crust flexes. Then as it moves away, it relaxes. Friction at the fault lines generates heat. Perhaps enough heat to melt ice within the faults.
Enceladus flexes its body, okay, and so that can produce friction enough to melt ice to create liquid water.
The prospect of liquid water on one of Saturn's moons demands further investigation. The first step is to determine the exact composition of the plumes. Mission Control fly Cassini just 30 miles above the moon's wrinkled surface, passing through the geyser's outer edge. Its instruments measure the composition. The results are completely unexpected. The plumes contain water vapor, nitrogen, and even simple organic molecules.
It doesn't take much of a jump at that point to make the association that if you have water, you have heat, and you have organic chemicals, you have the conditions that might actually produce primitive life.
Scientists now believe that Enceladus has conditions that can sustain life. Living organisms could survive around the warm faults that sit at its southern pole. The latest theories suggest that the faults in the terrain here may stretch down to a subterranean sea. This would be a dark world devoid of sunlight, but life may still have emerged here. On Earth, primitive organisms thrive in similar hostile and extreme environments. Scientists speculate that the same could be true of Enceladus.
There's the possibility of having something akin to those hydrothermal vents that we see at the bottom of the ocean. And we know there are living organisms there. There's chemistry that goes on there that living organisms can utilize to live.
It's a tantalizing possibility. If there are living things on Enceladus, the implications would be profound.
What could be a more important scientific discovery than to find out life has evolved separately in some other place? That changes the whole picture for human beings.
If we could demonstrate that the origin of life, Genesis, had occurred twice independently, then as far as I'm concerned, the spell is broken. We could safely infer life had occurred an astronomical number of times throughout the cosmos in its 13.7 billion year history. So this is why it is such a pressing question for us.
Cassini shows us that life may be possible on alien worlds. On April 15, 2008, more than 10 years after launch, NASA announces that the mission will be extended for a further 2 years. Parts of its tour will be dedicated to the exploration of Enceladus and Triton. Perhaps it will make the biggest discovery of them all: life on another world. 65 million years ago, a 1,000 billion ton asteroid smashes into the Earth, wiping out the dinosaurs. Massive impact events are likely to happen once every 75 million years. Today, scientists scan the skies for these giant killers. But an asteroid just 150 feet across could devastate a city the size of New York. Asteroids this size could hit any time. And right now, there is nothing we can do to stop them. It's a nightmare scenario. 1,000 billion tons of rock on a collision course with Earth, hurtling towards it at over 50,000 miles per hour. It hits with the force of 300 million nuclear weapons. Enough energy to wipe out every human being on the planet. This is no nightmare. It's real. 65 million years ago, a rock this size smashes into the Earth. And wipes dinosaurs from the face of the planet. It could be 10 million years before the next impact this big. But smaller asteroid impacts can also be devastating, and they happen far more often. Around 50,000 years ago, an asteroid slams into the Arizona desert, hurling 175 million tons of rock into the air. Meteor Crater is nearly a mile wide and 570 feet deep. Amazingly, the Canyon Diablo asteroid that created it was only 130 feet in diameter, about the size of a small jet plane. There are more small asteroids like this in space than large ones, and they can hit the Earth as often as every few hundred years. One scientist at Northern Arizona University thinks Meteor Crater has a message. Professor Ted Bunch.
Events like this, smaller events, they could happen anytime.
And they're capable of massive destruction. The extreme heat of this blast tore through the desert sandstone.
This is coconino sandstone, and it's in pretty good shape. And there's a piece here. This is also coconino sandstone that is severely shocked. Probably temperatures exceeding maybe 3,000 degrees Fahrenheit. Huge amount of pressures, and you can see the difference. This used to be this.
Imagine the same thing happening today. What would a 130-foot wide object like this do to New York City?
If this meteorite had hit Manhattan yesterday, about 80% of the people would have had serious injury or died. All the boroughs of New York would have been affected, either by the heat, the shock wave, the seismic activity, crumbling of buildings, and collapse.
Everything within a 5-mile radius would be obliterated. Asteroids have crashed into our planet ever since its formation. The key to their destructive powers lies in their mass and the speed of impact. As an asteroid hurtles towards Earth, it builds up huge amounts of kinetic energy, much like this speeding car. The faster the car goes, the greater the kinetic energy, even though the car's mass stays the same. When the speeding car hits a brick wall, it doesn't inertly stop. All the kinetic energy is converted into an explosive force. The crash generates heat, metal bends, plastic and glass shatter. An asteroid behaves exactly the same way when it impacts the Earth, only because it's traveling at 50,000 miles per hour, the explosion is far greater. Here in Arizona, evidence of the impact stretches 6 miles from the crater's edge. Pulverized rock particles called impactites shot across the landscape at deadly speeds.
We have impactites, all these little dark guys. Those are melt rocks. There's literally tens of thousands of them right in this particular area. These were ejected as far as 3 to 5 miles under very high velocities, 2 or 3 times the speed of a rifle bullet. But if you were an animal in this area and you had thousands of these particles coming at you, you'd be toast.
Impactites are a major clue to an asteroid strike and can reveal previously unknown impacts. Fossil hunters in Alaska uncover fragments of tusk from woolly mammoths. They are peppered with buckshot-like particles and date back 34,000 years to a time when the number of large mammals in the region inexplicably dropped. Have fossil hunters uncovered evidence of an undocumented asteroid impact? Dr. Richard Firestone searches for evidence.
We analyzed several of the particles from various tusks, and they had the unique signatures of meteorites. They were rich in iron and nickel, which is a critical component of most meteorites.
This is strong evidence that these woolly mammoths died from an asteroid impact. The force of blast was devastating.
We did an experiment with a shotgun to see what would happen if you shot a mammoth tusk, and they simply bounce off the outside. Nowhere near enough energy for that.
A shotgun fires at 600 miles an hour. Asteroid fragments travel over 30,000 times faster.
In order for the impact particles to penetrate the tusks as they did, they'd have to have been moving at tens of miles per second.
Firestone's mammoth died in an asteroid impact 34,000 years ago. The impactites embedded in the mammoth tusks prove that previously unknown asteroids have struck the Earth. And new evidence reveals that they didn't just kill mammoths. Humans died too. "13,000 years ago, North America is locked in an ice age. Large mammals like giant sloths and woolly mammoths roam the land. The nomadic Clovis people live alongside them. Then the fossil record stops. Many species of mega mammal abruptly disappear. What causes this sudden, mysterious disappearance? The Clovis culture also vanishes from the archaeological record. Is it starvation? Disease? No one knows for sure. Now a cave in northern Ohio may hold the answer. 30 feet underground, an archaeologist from the University of Cincinnati discovers evidence of an ancient catastrophe. Ken Tankersley and his team dig up a layer of burnt material in the soil. It dates to when the Clovis and the mammoths vanished. To archaeologists, this distinctive carbon-rich layer, called the black mat, indicates intense burning, a sure sign of a destructive event.
Beneath this layer, we have evidence of large mega mammals. Above it, there's none whatsoever. This mat was deposited in a very quick and sudden event. Beneath it, you have evidence of Clovis people. Above it, you have absolutely none. The real mystery is what happened at this very time.
What catastrophe caused this black mat? Tankersley searches inside the black mat and uncovers the bone of a wild pig, known as a peccary. It tells a disturbing story.
This particular bone has not seen air in 13,000 years.
The bone shows signs of extreme burning.
We know this burning is not the result of cooking. These animals were larger than I am, and to take a human body and a natural fire, you have to burn the body for days. This type of burning clearly came from a very intense, very fast burning, a single event fire, if you will.
Did an asteroid cause this deadly blast of heat? If it did, there is a vital piece of the puzzle missing. There's no evidence of a crater. This leads to a disturbing possibility. Could an asteroid be big enough to destroy an entire culture? Yet so small, it leaves no trace. Around 50,000 years ago, a small 130-foot wide asteroid smashes into the desert of Arizona and creates Meteor Crater. An impact this size could wipe out a major city. But this isn't the last time Earth was hit by a small but deadly asteroid. We're realizing that Earth is far more vulnerable than we once imagined. And some devastating impacts have left almost no trace. Archaeologist Ken Tankersley has found a black mat, evidence of an extreme heat event in a layer of rock dating back 13,000 years. The same time that the Clovis culture, one of the earliest in North America, abruptly and mysteriously vanished. Is an asteroid responsible? New research at sites across the United States also uncovers the black mat layer of burnt material, all dating back to the same time. The chemical analysis is compelling, but Tankersley wants to be even more certain. He returns to the Sheridan Caves in Ohio to take further samples. At the University of Cincinnati, an electron microscope takes a close-up view. Tankersley magnifies the tiny sample 10,000 times. He spots compelling evidence of a devastating asteroid impact. Detonation diamonds.
What's kind of tantalizing here is the possibility that these are associated with a cosmic event, if you will. Detonation diamonds are the result of a strong impact from either a large meteorite, an asteroid, or slice of comet.
Major asteroid impacts have shaped history more dramatically than ever imagined. It seems increasingly likely that an asteroid is the reason for the Clovis culture's disappearance 13,000 years ago.
In geological time, 13,000 years ago is yesterday. The implications for us living on the planet today, we always think it's not going to happen to us. The reality is when it's going to happen next.
No one has ever found a crater from this event. So the question is, how big was the asteroid that caused this catastrophe? Asteroids are mostly composed of rock and metal, debris left over from the formation of the solar system 4.5 billion years ago. Thousands of these objects orbit near the Earth, some as big as mountains, others smaller than a speck of dust. The size of the asteroid that may have ended the Clovis culture is a mystery. One scientist thinks he can find the answer. Professor Peter Schultz of Brown University starts with one vital piece of information. The Clovis culture ended during an ice age. 13,000 years ago, North America is partially covered in a layer of ice up to a mile thick, the Laurentide Glacier. So the question is, what happens when an asteroid slams into ice rather than land? Schultz suspects the asteroid would leave a crater in the ice, a crater that might eventually melt, hiding all evidence of the impact.
The fact is, ice was there, and there's no reason why an impact couldn't hit there as well as any other place.
Schultz tests his theory in the vertical gun range at NASA Ames Research Center outside San Francisco. The vertical gun is unique. It can fire projectiles at 13,000 miles per hour, equivalent to the speed of a real asteroid. Schultz must find the exact ratio of asteroid size to ice thickness to cause a devastating explosion, but leave no crater. He uses a tiny glass bead in place of an asteroid and a half-inch sheet of ice for a mile-thick glacier. The experiment will tell Schultz how much damage a half-mile wide asteroid would cause.
We got about 3/4 of an inch of sand in there. We're going to be firing a projectile about a 1/4 inch across, but the question is whether or not it's going to penetrate all the way through.
An asteroid colliding with Earth smashes into the atmosphere. Friction superheats it as it plummets through the air. Schultz simulates Earth's atmosphere by filling the chamber with argon gas. The gun will fire the projectile at almost 4 miles per second, the equivalent speed of most asteroids.
Every time you do an experiment, you learn something brand new. I love surprises, and invariably we have a surprise.
Could an asteroid be small enough to leave no crater, but big enough to devastate large parts of North America? It's a pressing question. The solar system is full of smaller asteroids. During the last ice age 13,000 years ago, an asteroid may have incinerated parts of North America, but left no crater. Scientists are trying to find out how an asteroid could be big enough to wipe out an entire culture and yet leave no imprint. Peter Schultz uses the vertical gun range to test what happens when a half-mile wide asteroid hits a mile-thick sheet of ice.
Oh! Pow! Oh my gosh! That's gotta hurt. Did you see that? Look at that stuff. Man, that hurt.
A glass bead enters the chamber at 13,000 miles per hour. When it hits the gas simulating our atmosphere, it burns and then explodes. A fireball smashes across the ice.
This is when you say, oh crap. It's coming for you. You can't even hear it because it's going faster than the speed of sound.
The experiment shows that a half-mile wide asteroid hitting a mile-thick ice sheet would have catastrophic consequences.
Oh wow, there's no crater. You don't even know that it happened. Let me go ahead and take some pieces out, okay? Here's where one big mass hit. You can see the little pit in there. If the ice hadn't been here, we would have formed a crater about that big. The ice acted like a flak jacket. You know, once this goes away, once the water goes away, you can't tell that anything was here. That's remarkable.
The after effects of the impact would have been felt as far away as Europe. But the asteroid itself leaves no crater.
All you need is an object about a half mile impacting into that. It might have formed a crater 20 miles across, but when the ice disappeared, melted, went away, you might completely remove the evidence. It's kind of like a perfect cosmic crime.
The asteroid that may have ended the Clovis culture could have been just half a mile in diameter. An estimated 1,000 asteroids of around this size hover near to Earth at this very moment. Scientists decide to look at other more recent impacts in order to reevaluate their size. One of the most famous and powerful recent asteroid impacts is known as the Tunguska event. June 30th, 1908, an asteroid explodes over Tunguska, Siberia with the force of 1,000 atom bombs. Tunguska is so remote that it takes 19 years for scientists to mount an expedition to examine it. The team brings survey equipment to record the devastation. The blast tore 60 million trees out of the ground. 800 square miles of Siberia, an area 1.5 times the size of Oklahoma City, are flattened and scorched. There is no crater. The asteroid exploded before it hit the ground. The size of the asteroid remains a mystery for almost 20 years. Then in the 1950s and 60s, impact specialists attempt to simulate the strike using data from nuclear tests. Some scientists estimate the Tunguska asteroid was up to 600 feet across. That estimate has been reduced to around 200 feet. In 2007, Dr. Mark Boslow reanalyzes the data using a supercomputer. He thinks the asteroid is much smaller.
Most of us had been thinking that it was an asteroid, came streaking in, it got down to about 5 miles above the surface and exploded with an energy of between 10 and 20 megatons. So we knew roughly what the wind speeds and what the thermal effects would be on the ground for an explosion at that height and that magnitude. And what was observed at Tunguska was consistent with that.
But this theory assumes a nuclear weapon and an asteroid impact in the same way. a nuclear weapon explodes from a single static point. But an asteroid is different. It's moving fast. So when it explodes, the energy it releases keeps moving, causing even more destruction.
When it explodes, it vaporizes, it begins to expand. It's very much like a nuclear explosion, except it's got a lot of mass and it just keeps on moving.
So the explosion over Tunguska spread out across the landscape.
We realized that even though it explodes at this high altitude, that explosion continues downward. All that hot rock, all that vaporized asteroid material continues downward, and finally it slows down and finally stops a few miles above the surface. The blue color here represents the shock wave, that blast wave that carries mechanical energy down. So that's very high wind speeds, hurricane force wind speeds. So when that hits the ground and sweeps across the ground, that's blowing trees down.
The old model assumed a stationary explosion. That meant a 200-foot asteroid. The model was probably wrong. A moving object could be small and still cause that much devastation.
The Tunguska event could have been caused by an asteroid as small as 100 feet in diameter.
Boslow's findings sent shockwaves through the scientific community.
There are many more smaller asteroids in Earth-crossing orbits than there are larger asteroids. Therefore, if Tunguska was from a smaller asteroid, a Tunguska-like event is more frequent than we had previously thought.
Scientists once thought an asteroid around 600 foot wide caused the obliteration of Tunguska. A rock that big hits Earth once every few thousand years. Now they've downgraded the size of the Tunguska asteroid to just 100 foot across. These hit on average every few hundred years, and the last one we know of was in 1908.
The most likely scenario for a big destructive impact event is from a Tunguska-sized object.
It's a game of chance. Another Tunguska-sized asteroid might not strike for another 100 years, or it might strike tomorrow. Luckily, the Tunguska asteroid hit in an unpopulated area. In today's world, we might not be so fortunate. The question is, what can we do to protect ourselves from asteroids, big or small? In 1998, the US Congress instructs NASA to take action. It sets up the SpaceGuard survey to identify and track any near-Earth asteroids that pose a threat to our planet. The first step is to identify the asteroids at least 3,000 feet across, the ones big enough to cause massive destruction if they ever hit Earth. So far, 1,100 asteroids this size have been located. The Catalina Stewart Observatory at the University of Arizona is part of this SpaceGuard network. Asteroid hunter Ed Bayshore and his team comb the skies for these giant asteroids.
Essentially what we need to do is we need to image an area on the sky 4 times over the course of about 40 minutes.
The computer takes 4 telescope images of the same patch of night sky. The stars stay still. But near Earth objects, the asteroids, move through frame.
So for instance, here's the first image of a field that we just observed. There's the second image, there's the third, and there's the fourth. When we start it blinking, we can see that we have an object right here in the field. As it turns out, that is probably an NEO by the way it's moving.
But what about the smaller asteroids? The ones we think wiped out the Clovis culture or exploded over Tunguska? Right now, Bayshore doesn't search for them at all.
There's many more objects that are smaller. And just because they're smaller doesn't make them not dangerous. In fact, we think the objects around 300 feet in diameter and larger, which are much more numerous, may actually represent a considerable threat.
Now, space scientists are determined to track these smaller asteroids. Among them is a man who is no stranger to the hazards of outer space, former Apollo test pilot Rusty Schweikert.
Now, it's very important that we start looking for these smaller ones because they hit with much higher frequency. From 100 to 150 feet in diameter and larger, we can start having serious effects on the ground. They are huge in terms of natural disasters.
The smaller the asteroid, the harder they are to find. They move at around 50,000 miles per hour in orbits that are extremely hard to track.
Because we've only been looking for the biggest ones up until this time, our telescopes really aren't adequate to give us the information, the early warning that we need on the smaller objects.
Tracking small asteroids requires specialized telescopes. These are still years away from completion. But occasionally, astronomers get lucky. In 2004, they pick up a moving object in the sky. Closer inspection reveals it's an asteroid, and it's 900 foot across. Researchers name it Apophis, after the Egyptian god of evil and destruction. It is big enough to destroy an area almost the size of Texas, and it is coming our way. In 2004, at the Kitt Peak Observatory, Arizona, scientists spot a new and relatively small asteroid. It looks like it is on a collision course with Earth. It is called Apophis, and it's 900 feet across. Around 10 times the size of the asteroid that created Meteor Crater in Arizona. At the Massachusetts Institute of Technology, Dr. Richard Binzel tracks its trajectory.
An impact the size of Apophis in terms of the immediate damage would be regional, roughly the size of France in terms of its immediate catastrophic effects.
Based on initial observations, researchers believe it has a relatively high chance of hitting Earth in 2029. The asteroid poses a real threat. Binzel needs to discover what Apophis is made of. He studies the asteroid via a remote link to a telescope in the Mauna Kea Observatory, Hawaii.
The instrument we're using is a spectrometer. The different minerals that are present in asteroids have very critical absorption bands, or very fingerprints, if you will, in these wavelengths of light that let us distinguish between different kinds of compositions, different kinds of minerals.
No two asteroids are the same. Most are solid, but some are loose piles of rubble. The majority are made of rock, but some are composed of metals and other materials. Apophis turns out to be mostly made of chondrite, a type of rock.
We think that Apophis is like this type of meteorite. It's an LL chondrite meteorite. And the beauty is that we can measure the properties of this meteorite in the laboratory. And if we scale this meteorite up to the size of Apophis, which we think is about 900 feet across, the mass of Apophis is about 20 million tons. The energy that it would have if it hit the Earth is about 375 megatons, the kind of energy we usually talk about with nuclear arsenals. And that's more than 20,000 times the energy of the blast at Hiroshima.
With the asteroid's speed and orbit mapped, researchers can predict its trajectory more accurately. New data suggests that the 900-foot asteroid is headed this way in 2029. It will miss Earth by just 18,000 miles. A near miss in astronomical terms. But if Apophis had been on a collision course, what could we have done? The most obvious solution is a nuclear bomb. The theory is that a blast could shatter it into pieces. But this approach is risky. The blast fragments could continue on a collision course with Earth. And to make matters worse, they are now radioactive. Instead of eliminating the risk, a nuclear explosion could increase it. Earth could get hit by a cosmic shotgun blast, resulting in even more widespread devastation. One scientist alarmed by this scenario is Dr. Massimiliano Vasile of the University of Glasgow in Scotland.
What could happen is that the shock wave due to the explosion of the outer crust fragment the asteroid. So it might be that basically we have not just one asteroid on the collision course with the Earth, but we have 2 or 3 asteroids.
Scientists are racing to find a better solution. They have suggested attaching rocket engines to push the asteroid off course, or even solar sails to pull it into a different orbit. These are possibilities, but they sound like the stuff of science fiction. Researchers are putting their weight behind a more feasible solution: knock the asteroid off its collision course. The project's code name, Don Quixote. At the heart of the team is space mission analyst Chris Saunders from Kinetic Labs, England.
We are simply going to try and hit the asteroid and deflect it out of the way.
The theory is that a powerful strike delivered by a probe could knock the asteroid off its course, like a game of cosmic pool. Don Quixote is a 2-stage spacecraft made up of the impactor and the orbiter. The ion engine powers the orbiter to its target. Solar panels create an electric field which ionizes an ultralight fuel load of xenon gas, ejecting ions from the engine to thrust the craft towards the asteroid at up to 200,000 miles per hour. The aim is to catch the asteroid as far away from Earth as possible, so that even a tiny push will move it off course. The observer locks into orbit around the asteroid and guides the impactor to an inch-accurate surgical strike.
It would move the asteroid's orbit by maybe 50 to 100 meters. That would be enough for the asteroid to safely drift past the Earth.
If astronomers locate an incoming asteroid early enough, Don Quixote might be able to deflect it. But it's untested technology with a huge margin of error. Most scientists agree a backup plan is essential. To defend Earth from an asteroid strike, scientists have an ingenious and radical approach. Use an intense ray of light to vaporize part of the asteroid's surface, creating a jet of gas that will move it off course. It's a good theory, but right now the only place Massimiliano Vasile can test it is in the lab. He uses the Industrial Laser Lab at Glasgow University to gauge how much light energy it takes to move an asteroid.
We can see the effect of the light of the laser that basically was burning the rock. This is what we expect would happen in space when we focus the light of the sun on the surface of the asteroid. The fact that I obtain is exactly as if I had a rocket engine attached to the asteroid, but the difference is that the engine is the asteroid itself. This is in fact one of the most effective ways of deflecting the asteroid.
But shifting a full-scale asteroid would take a lot more light than an industrial laser. Luckily, in space, we have a huge power source available: the sun. Vasile proposes using mirrors to focus sunlight on the asteroid, enough to vaporize its surface, just like the laser. But moving a 1,000-foot asteroid requires a mirror so large that no rocket is big enough to carry it into space. The solution? Use several small ones at once.
We propose to have a swarm of satellites, each one carrying a smaller mirror.
The mirrors would be around 60 feet across and precisely shaped to concentrate the solar energy, creating that vital jet of vaporized rock. Whatever system scientists end up using, the key is to catch the asteroid as early as possible. Astronaut Rusty Schweikert thinks it's vital to be prepared.
Even you and I driving our car, you know, you and I typically have one chance in 10,000 that we're going to have an accident tomorrow if we're driving tomorrow. And because of that, we buy insurance. We're driving around the solar system on our planet totally uninsured. Why?
Someday, humanity will likely face another asteroid, like the one that exploded over Tunguska, or wiped out the Clovis culture. An asteroid just 150 feet across could kill tens of thousands of people, and we still don't know enough about them. The dangers and our lack of knowledge became all too apparent in September 2007. Carancas, Peru. Local people noticed strange lights in the sky, followed by a huge explosion. Villagers stumble on a 50-foot wide crater in the highlands. Locals claim it is caused by an asteroid, but not all scientists are convinced. Impact specialist Peter Schultz thinks it's a hoax.
My immediate reaction was, are you kidding me? This has really happened? It can't really be something that actually got through the atmosphere. This is science fiction. And the first pictures that came out, it looked like a B movie with this crater where Superman was going to walk out.
Schultz is disturbed by the size of the crater. It's tiny. An asteroid that small should never have made it through the Earth's atmosphere. It should have burnt up on entry. September 2007, a fireball blazes through the skies of the Peruvian highlands. It crashes to Earth near the village of Carancas in southern Peru, leaving a crater 50 feet in diameter. Eyewitnesses are mystified. At first, they think they're under attack.
We looked up at the sky and saw a smoky trail. First we thought it was a military plane. Then we saw that the object was approaching the ground, heading south. The workers said to me, I think that plane is out of control. We were really scared. Even animals were running away due to the loud noise.
One explanation is an asteroid strike. But how did an asteroid so small survive entry into the atmosphere? It should have disintegrated before impact. Peter Schultz, one of the world's leading impact specialists, travels to the site to investigate.
I heard the stories in the media, I saw the pictures, and I thought, oh my gosh, I've got to go there.
The impact has blasted chunks of Earth into the air, damaging a building 150 feet away.
Wow. Oh, jeez. Oh, my gosh. Wow.
Whatever caused this crater was powerful enough to blast 100 tons of soil across the landscape.
This is clearly the pre-existing soil. Everything was just simply turned upside down over this.
This has all the hallmarks of an asteroid crater, but Schultz is skeptical. He needs to find a fragment to prove it. He exploits a common characteristic of this kind of asteroid, its magnetism. The metallic fragment and the shape of the crater convinced Schultz that this was an asteroid strike. But how big was this asteroid? Eyewitnesses tell Schultz the angle of impact. Now if he can discover the speed, he should be able to discover the size. At the NASA Ames Research Center, Schultz examines the fragment of asteroid under a powerful microscope. It reveals the true story behind the impact.
The fragments were deformed. There were fractures, and they were in a pattern that happens at around 3 to 4 miles per second, almost 5 times a speeding bullet.
Schultz now has all the clues he needs to figure out the size of the asteroid.
From those pieces of information, the angle and the speed, we can determine how big it was. And it's probably somewhere between 3 feet and 6 feet.
It's an extraordinary discovery. Up until this moment, scientists believed rocky asteroids this small burned up before they hit the ground.
Here we have a puny thing, only about 3 to 6 feet across, that somehow made it to the surface. This shouldn't have happened. This just shouldn't have gotten through the atmosphere. In this case, it made it through. It not only made it through, but it hit hard.
How it got through exactly is still a mystery, but the fact that it did is alarming. If a tiny asteroid like the one that hit Caracas strikes a crowded city, it could potentially kill dozens, if not hundreds of people.
Will it kill people? Yeah. The clock is ticking. It's coming.
This is not one of those giant things. This is the type of thing that if it happened in New York, it would have caused some serious damage. It probably would have gone right through the ceiling of a tall building and gone through about 4 or 5 floors before it rested.
In Peru, we were thrown a hypervelocity curveball.
Rusty Schweikert believes that now is the time to take the threat from smaller asteroids seriously.
A hurricane, we can't prevent. A flood, we can maybe do some things to prevent. We can certainly mitigate against these things. But preventing is an unusual opportunity in a natural disaster. We can prevent this from happening. If we do our work with near-Earth objects, we can prevent asteroid impacts from ever happening.
There is little doubt that an asteroid will someday threaten the Earth. The question is, will we be prepared to deal with it in the not-too-distant future?